I hope everyone is okay with recording. If not, let me know. We can deep fake you out. I'm joking. So yeah, so you will be able to find all the recordings on our website. Also, I encourage you to join our Slack workspace where you can talk about where you can discuss or ask questions about each individual paper or any other questions that you have. And I will post the link on the chat here on Zoom. And yeah, so without further ado, I will give the floor to Sylvia, which will start our first session. Sylvia, it's all you.
Yes, thanks for the introduction. And now let's introduce the first paper and the first session of contributions from the authors. So we are demonstrating the impact of modeling decisions. Do Alan and Ron, or are they here? Alan? Otherwise we go to the second. Yeah, perfect.
Yeah.
So then feel free to share your screen. And yes, so the paper is demonstrating the impact of modeling decision, and it's with Alan Lindsay and Ronald Patrick.
Yeah, can you see my screen?
Yes.
Cool. Okay, cool. This is work done at Heriot-Watt University with Ron Petrick. It's called Demonstrating the Impact of Modeling Decisions. So it's kind of shares the idea with other work of there being a user model and an agent model. And the typical assumption has been that we are trying to correct the user model. I guess at least it's possible that in small areas, at least, that the human might actually have a more accurate model. And they might be surprised by what the robot does because of that fact. So the kind of the modeling selection process, we kind of start with a model, and then we have to simplify or refine it depending on some kind of criteria. So here we're going to assume that we've got some features that we're going to that are going to capture what we care about in that sense. So things like, so if you basically just want to be able to replan in time for reaction time, then computational time might be important. But there might be a whole range of other things. If someone has to actually read the PDDL, then this might be important too, right? And I guess now that we're starting to see more kind of automatic processes for moving between these different languages, it's kind of interesting to consider it as a search where you could actually hope that this could be done automatically. So we're going to, for the purposes here, just assume that we've started with a really rich model and we're just going to do some simplification steps. And because for simplification as well, we're going to assume that we can kind of move around. We've got mappings between the structures and these different things, right? Okay. And at some point we satisfy some criteria over these features, and our agent is then given the model, in this case MI. So examples of what these might be: abstractions, discretizations, determinizations. So simplifications, but also, I mean, I'm not going to talk about refinement here, but this list goes on with, enhanced predicates or process refinement. So some examples that we've seen in macro actions, model simplifications, arity reducing, continuous to discretize, things to get rid of uncertainty. This continuous to discretize could be in temporal, or it could be in variables. So it's typically we haven't really thought too much about the automatic sense of the simplification or refinement of the model as kind of satisfying some requirement, but these are typically thought of as just making our search or making our planners solve more problems. But you know, it's kind of interesting to think about it in that sense as well. And we're making these steps here just to satisfy some criteria. Okay, so of course these steps have implications in this example. Just going to focus on the abstraction step. And so, for example, here we've combined these two states, and this is a bit of an obscure example, but I think it's simple enough to kind of highlight the point. And we've got some properties, right? So an optimality impairing modeling step is where some of the plans are going to have the opposite order relatively, and a sequence pruning modeling step is where you've got some precondition modeled in a state. For example, his visible here is modeled here for the robot at Y, but when XY is made into one location, then it's no longer visible. Okay. So the specific scenario we're looking at is the agent is proposing a plan and the human's suggesting some other plan, and we're basically assuming that the model here that the human's using, sorry, that the agent's using is more limited than some model that we can map the query of the human onto, right? And we're going to just identify some properties to give the human more understanding about why their plan has been kind of demoted against the robot's plan. So for example, that the agent's plan is actually a plan in the simulator or in the model, that there's a reason why their plan was less kind of good in the agent's model, and there's a justification for the actual steps that we're taking here. Okay. So, I mean, this can be a set of features with some criteria, right? So the explanation of or kind of justification here might vary, but for this example, it's just simple computation cost, and in this case, this model was just too expensive, whereas this model, so this is the richer model that the human's plan could be mapped into, whereas this is the more limited model for the agent, and so the computation cost is less here. The agent's plan, which is this one here, which takes an extra step to Z, can be mapped into a plan for the richer model, as you can see here. And then the human's plan, you can see that it's fine here. We can see the tree. But when we take it into the agent's model, we see it's not a plan. And we can also search for example of this state here to show to demonstrate like the human, the kind of states that we're getting composed here, basically. So this is kind of providing some justification for why their plan is, in the agent's view, is a bad plan, right? And this could be a cost thing, or it could just be the fact that in this case it's not a plan. So the first step we've taken is to kind of look at visualizations, and in this case a property visualization, and the generation of these extra states, right? So in this case, we're looking for a state that's mapped from one of these, from this state, sorry, a location that's mapped from this location, and also a location where the robot's at that location but cannot see the tree, right? So we're searching for that. It's different ways to find these states, so there's more details there. But in this case, we've got this, the property is satisfied, so we can visualize it, the field of view of the robot seeing the tree, where in this one it's not. So it's clipped. Okay. So basically, modeling includes a model selection stage, which considers steps such as abstraction or determinization that are made in order to optimize some factors. These steps impact on the agent's model and the perceived quality of the plan selected by the agent. And we've kind of talked about some modeling steps and presented some approaches for demonstrating how these impact. So how the user might understand the plan in context of the comparison between their plan and the robot's plan. In the future, we're going to consider how to combine this with other types of explanation, because obviously one kind of issue is that there might be different ways of explaining the same thing, right? So how do you balance these different explanations, and also how to communicate different communicate plans that are from different models, so that the human actually understands what the context is at each point. Okay, cool. Thanks.
Okay, thanks a lot, Alan. Do we have any question? Do you have questions? You can raise your hand if there are questions, or just speak. Otherwise, I'll ask a very quick question. So when you explained about the abstraction step, I was wondering about how do you perform this abstraction step, and if you can tell a bit more about the modeling steps in general, because it's not very clear to me how your algorithm identify the modeling steps.
Yeah, I mean, it's a kind of theoretical thing, right? I mean, so there are different approaches to making some of these modeling steps, right, that exist in the literature. So there's different ways of abstraction, for example, or recent work going from continuous temporal to discrete temporal. So there's different steps that exist, and I guess they don't exist I mean, actually, in reality, this is typically a human process where you start with a model and you find that you can't actually use it, and so this is just a start to kind of put some bounds on that process, basically.
Okay, let me double check if I understand. So you mean this is kind of more high level, so it's not important which type of algorithm do you have, it's just that you need to have those specific steps. And
well, I think it definitely does depend. I mean, you know, so if so I was looking at abstractions here, but and actually probably more relevant to certain things that happen when you relax for resources or something like this. So because the specific abstraction step I looked at, the reason why I was calling it peculiar is because you are you usually like to retain plans when you abstract something, whereas I don't have that property here, right? So if you imagine, I don't know, like the match domain, where you strike a match and you have to get across the basement, and you've got two different ways of doing that, and one doesn't, you can't do it within the match, and one you can, right? So in that case, you if you want to abstract these two states or structures, you might want to do that in a safe way that says that neither, just this plan can't happen, right? So I mean, and that's just abstractions, but if you determinize something, then the types of explanations for that are probably going to be different, right? So it's a start to look at, right?
Okay.
Yeah, because I mean, so I don't know if we have enough time for another question, but
yes, we do.
So Yeah, I mean, I don't know whether it's just a semantic difference in what you determine to be an abstraction, but I always think of abstractions as something that increases the space of plans rather than reduces it. So, I mean, what do you gain from allowing abstractions that make the problem more difficult?
Well, I mean, it's potentially a balance, right? I mean, so macro actions can potentially make planning much more difficult, right? They're not an example of well, if you add them on top of the normal actions, then they're not an example of where you lose plans. But you know, it's potentially, so in this example, I mean, you know, I got rid of the state, and I mean, these were the numbers for the you know, that I made a problem, and these were the numbers that I observed. So, you know, I mean, obviously these numbers are quite small. When you go from like a continuous, so if you imagine you have a temporal space or you know, continuous space, you've got to make decisions that potentially, you know, so for example, if you've got to get to some place, and your waypoint is kind of in the middle of the room, and you have to go all the way to the middle of the room, then that means that you might not have enough energy anymore, and you might have to go somewhere else to get energy. Then it was basically the modeling decision that put that waypoint in the middle of the room rather than on your path between the 2 points you want to go to, that has led to this situation where the user can then look at that and think, well, I would have just walked, you know, it's got enough energy to get there, just go for it. So it's that kind of situation, right, where you.
Okay. Yeah, I think so. Maybe we'll talk offline a little bit more about it. It is interesting about these abstractions. Did Tathagata raise his hand as well? Or?
Yeah, I just had a quick question about the domain. So I remember a couple of years ago you were doing some experiments on an interface for bike ride sharing, sort of that sort of domain. I was wondering if you saw like examples for the need for this sort of modeling in those interactions from the.
It's a good question. So from the determinant, so I mean, it was a partially observable domain, and I think that's you know, it's definitely is. There's these situations where, I mean, actually they're quite often potentially planning decisions, right, that interact with the modeling decisions, which make it, you know, this is my future work.
Is Alan stuck or?
Oh, I think we've lost him.
Oh.
Yes, because yeah. Okay, maybe we can also continue with the question on Slack.
Yeah.
And we can move to the next paper presentation. I kindly ask Alba. Alba, you here?
Yeah.
Perfect. So Alba will present a paper, Repair Suggestions for Planning Domains with Missing Action Effects. And the paper was done in collaboration with Angel Garcia Olaya and Fernando Fernandez. So if Alba, you want to share your screen?
Yeah, I'm doing it. So can you see my screen?
Yes,
yeah?
I can.
Okay. So perfect. So hi everyone. Can I start? Yeah. Okay. Thank you. So hi everyone. My name is Alba, and I'm going to present a joint work with Raquel, Angel, and Fernando called Repair Suggestion for Planning Domains with Missing Action Effects. So first of all, I'm going to introduce the problem and the motivation behind it. Then I'll define the problem and the classical planning compilation we have created to solve it. And finally, I'll comment the experiments and the main conclusions of the work. We use the type planning formalism to specify planning task, where a planning task is composed of a domain and a problem. And in this work, we are especially interested in the domain, which is composed of a hierarchy of types, a set of predicate symbols, where one of them is an NR predicate, and a set of action schemes, where each one is composed by a set of preconditions, positive and negative effects. So this definition is used to specify a lifted formal model in a common planning language like PDDL. But however, defining formal models is tedious and time-consuming, reason why it's very easy to make mistakes which can turn the planning task unsolvable. Some works in literature have dealt with this problem, and some of them assume a domain and a problem, but also a plan which is broken, and they provide some advice on how to fix it. And for the cases where we don't have a suggested plan, some works focus on explaining why the plan has no solution, or try to provide an alternative initial state from which the plan is solvable. But we consider that just making changes to the initial state is not enough in some cases, because if we consider, for instance, the well-known barman domain, where a robot prepares drinks using glasses that need to be empty and clean to be filled, for instance, forgets to include the action effect that cleans the glass, which turns the task unsolvable. But setting the glass as clean in the initial state will not solve the problem, because the glass can be get dirty again. So a better option would be to repair the operator and allow the robot to clean the glass. But due to the number of potential changes to the set of operators, repairing these faulty domains is not trivial, and previous works focusing on incomplete domains assume some guidelines from the user side to supply this lack of knowledge. But we think that if a user makes a mistake in the model, he's probably not even aware of it, so we can't ask him to say where he has made a mistake. But in fact, what we can do is identify that he has made a mistake because the task has no solution, and repair the broken domain through what we have called a uniform repairing problem. But as a better option, we can show him some suggestion on how to fix the domain. And in this way, what we propose is to deal with the incomplete planning domains without further help of the user, but with his supervision. We are almost starting this work, and we make the strong assumption that the domain is broken because some of the actions of the domain lacks a positive effect, because we think that this error is the most likely to turn the planning task unsolvable. As we have shown before, if we have the clean shot action broken and none of the other action of the domain can clean the glass, the task will be unsolvable. So the objective of our uninformed repairing problem is to find the set of atoms to extend the effects of the actions in a way that we obtain a new repairing domain which can solve the task. So let's imagine that our domain has some missing positive effects in the action clean shot and fill shot. Then our objective is to find these errors, this lack of information, to repair it and make the task solvable. To do so, we propose a classical planning compilation of the planning task to a new one, extended planning task, in which we have reformulated the domain types and the action, and we also have included new predicates and new actions, new operators to repair the domain. In this way, the domain can fix itself by applying these operators. And of course, we also adapt the problem to allow this reparation. And in this slide is the main idea of our compilation. So first of all, we have created a new hierarchy of types to include the planning elements, as we can see here, action and type domain. And this type, called item, involves the elements we use to repair the domain, which are predicates and objects. And this type, object domain, also includes all the original types of the underlying domain. Then predicates are now represented as domain objects. So in this way, we can group predicates with the same arbitrary through another predicate called in-state. Then, while in the original domain, the information was represented with common predicates, our compilation indicates which information is true in the current state. So we don't represent clean or empty SOT, but in a state clean SOT1, for instance, where the first parameter is always of the type predicate and the rest are of the type of the domain. And with this approach, we can add predicates to the current state in a general way. According to this, we compile every action in the domain to adapt them to the representation. And we also include information about which objects use its action. And in the same way, we also reformulate the initial state, also adding information about the current action and effect and new goals, indicating that every action has to be checked for errors during the search. Once the planning task is compiled in this way, we also include into the domain new operators to repair the planning task, as I said. We provide two different actions, where one of them detects the error and links an action with a missing predicate through the fetch fix, and another one applies the reparation with the objects currently used in the action. So we have two operators, and to illustrate it better, we have here a part of a plan in which we can see how, first of all, the action clean SOT is fixed with the clean predicate, and after that, it applies the repair operator to add to the state the predicate with the proper object with its SOT1. Then, after that, if the glass needs to be cleaned again, it only has to apply the repair operator because the action was previously fixed in this step. So this is the reparation that would be suggested to the user, to repair the action clean SOT with the predicate clean. But however, this reparation cannot be accurate, and during the progress of this work, we have identified some issues related to the reparation. Because since the task is unsolvable and we provide operators to add new information to the state in order to make it solvable, the easiest way to do so is to directly add the goals. By this reason, we have to introduce a metric to penalize undersized reparation. Another example is related to domain invariants. For instance, in this action, in clean SOT, this action already set the glass as not clean in the effects, so it wouldn't make sense to repair this action with the clean predicate since it already contains it as a negative effect. So as I said before, we penalize this kind of reparation in an attempt to get as close as possible to the reparation and to the domain decided by the user. Regarding to the experiments, we have selected 4 domains from the planning competition, and we generated 10 problems associated to them. For each domain and problem, we have followed an iterative process in which we broke the domain by removing just one positive effect, 2 positive effects, and so on, until a maximum of 5 removed effects. So for all the cases, the resulting planning task was unsolvable, so we performed the compilation to solve the uninformed repairing problem, and we compare the repairing domain of time with the original one to see how was the reparation. To run the compile task, we had used the LMCAT and Llama configuration of Pathfinding, and in most of the cases, we achieve almost 100% of success rate compared to the original domain. But however, it presents scalability problems in larger instances. But maybe we have realized that maybe this is not the best experimental setting. So for future work, we want to run them again, but using the LMCAR configuration to prove that we can provide suggestions in a reasonable time, no matter the success rate, and use the llama configuration with users to measure how accurate is our approach and the number of attempts needed to repair the domain as the user wants. And finally, as a conclusion, I think that we can say that the method performs well for a wide range of planning tasks. And anyway, inaccurate reparations can be supervised by users, like in an iterative process. So we think that the method has enough potential to be considered like a support system to develop planning tasks. And as a future work, we would like to run again the experiments, as I said, and we think that it is also possible to to perform a pre-process of the planning task to detect unreachable preconditions and improve in this way the scalability of the approach. And we are also thinking about automatically generate a set of problem instances to repair the domain for a wider range of problems, instead just for one, which can be seen like a weak reparation. And that's all. Finally, I want to mention that according to the reviewer suggestions, we are working on totally change the formal description of the paper. So if any of you are interested in the work, I would like to ask you to wait for the final version of the camera ready. And that's all. Thank you so much for the attention.
Thank you, Alba. Thanks a lot. Do we have any question? I can hear someone talking, but maybe it's... yes, we have two questions. Yeah, two raised hand. So I don't know who was first, but we have Christian and Alison. Please go ahead, Christian.
Access your paper for it. I'll ask quick. One, this is really interesting work. Thank you for presenting. I'd be curious to see some of these benchmarks of broken domains sort of captured and released. It would be really fun for the community to start building a repository of broken PDDL. I have an interest in that. But my question is around one comment that you made that a common error might be a missing add effect. If I had some prior knowledge of what common errors are in my domain, is there any extension that you see where I could change the optimization function in the encoded planning problem so that it would find errors of a particular form more than errors of another form? Say I happen to know that this particular predicate, the modelers of this domain typically forget it more often than another predicate in their add effects, right? So could I put that sort of preference function inside of the encoding to find errors that are more likely given my own prior knowledge?
So you mean if the user can parametricize the way in which the task is repaired?
Yeah, or to give preferences over the type of repairs that it would suggest first. All repairs being equal, I might say that these repairs I would like to see more because this is more likely to be the real issue than these other repairs in some sort of way.
So as I mentioned, we have seen several problems with the reparation, and actually we don't have control it, but we have estimate a cost, because the most penalized action is to directly add a goal. After that, to add a domain invariant. After that, to repair, if I have some missing effects in different actions, to repair all of the effects in the same action, like creating a macro operator. But maybe a user can say, okay, I prefer to repair all of them in the same action, maybe. So we want to give the user the opportunity to parametricize the how they want to the reparation is done.
Nice. Yeah, because we could start to channel then the common errors that are made into the cost function for the repairs inside of this domain. So anyway, thank you. Thank you.
We have estimated the cost function, but it's like we are almost starting the work. We have to profundize in that. So, but every comment is welcome. Thank you so much.
Thanks.
Okay, so Alison, do you want to ask a quick question now?
Yeah, hopefully it's a quick question. So what are, maybe I missed this, but what are some of the reasons that users end up with incomplete domain models like this? Like from like maybe the user experience community or from the cognitive science perspective on this problem that you know of?
You mean why users can create an incomplete model?
Yeah.
I put it in this. So actually, the background is because we have like we are developing like a tool in which a non-expert user can define a planning model. And we have me as a teacher working with a student working in planning, we have seen that most people, when they try to build from scratch a model, it's very common to make mistakes because actually maybe you don't know how the domain is. Maybe you have some scheme in your head that that doesn't fit with the real world, and I don't know, we assume that it's very common to make mistakes, especially if you can forget some positive effects. We are starting from positive effects, but actually a user can forget a precondition. They can add more preconditions. This is our future work to extend the work to more elements in the planning model, but we assume that it's very easy to make mistake when developing a planning model.
Okay, so these are the reasons based on your observations of a student, like a student new to planning. Okay. All right, thank you.
And from myself, of course.
Thanks a lot. So if you have any other question, please join the Slack channel. We have a specific space for extra question. It would be nice to continue the discussion about the papers. So thanks, Alba, once again for your presentation. Now I'll ask Yotam, if Yotam is here, or Guy, or Ofra.
I am here.
Perfect.
But you need to stop sharing.
Sorry.
Yes.
I don't know. Okay.
Next, thanks, Alba. So next presentation will be about interactive explanations of agent behavior. And okay, so it will be Guy presenting, and the paper is also from Yotam Amitai and Ofra Amir.
Yeah. So thank you. So Yotam was indeed supposed to present this, and for personal reasons he couldn't come. So I was given the task of presenting this. This is, so another word before I start. So this is joint work with Yotam and Ofra. Yotam, this is an interdisciplinary work. So Yotam and Ofra come from Explainable AI, and I come from a completely different field called formal verification. We'll talk about it during the talk. So this is, so I apologize if I don't cite your work. I'm basically layman in Explainable AI. Okay, with that I will start. So we're going to talk about agents that have been trained using reinforcement learning, using RL. I assume that you know this, but at a very high level, I'm going to describe how RL works. So basically the way this works is that there is an agent here represented by Homer, and what he does is basically act randomly during training. So he gives actions to the plant. This is sometimes called also the environment, and the environment produces states and also rewards during training. And the goal of this agent is to maximize, to learn how to produce actions so as to maximize the rewards. And this is a very successful paradigm. Yeah, I should say that we focus on deep reinforcement learning, and in which the agent's policy is given as a neural network. This is a very successful paradigm. It has been applied to, for example, board games, where the environment in each point in time outputs the state of the game, so where the pieces of the chessboard are placed, for example. And then what we want to do is train an agent or train a policy to win the game, win the board game. So this has been successful in chess and in Go recently and so forth. Another success story of RL is Atari games, where again the state is basically a screenshot of the simulator, and the reward is the score in the game. And the action is again how to design a policy that wins this game. It's been applied in finance applications, in healthcare, in robotics, and many more applications. So why use RL? So it's extremely successful. It produces, in many of these domains, it produces agents in which the performance exceeds human capabilities. But the problem, especially in deep RL, is that these agents are uninterpretable. So basically, they're black boxes, and they're unpredictable in very unpredictable. They can be wrong in very unpredictable places, and there's no guarantees on these agents. And this is especially problematic if we're talking about the last two applications that I mentioned there, where these are so healthcare and robotics. Take, for example, self-driving cars. So these are safety critical domains in which we want to trust our agents in order to use them. So this is the motivation for this work. So the goal is how to explain RL trained agents. This is what we're talking about. Okay, so again, you know more about explainable AI than I do, but still there is a challenge that comes from RL trained agents, which is unique to these types of agents, specifically that the environment is dynamic. These agents interact in an ongoing manner, in an ongoing and stateful manner with the environment. And so there's a distinction between local and global explanations. Basically, these types of agents are inherently local. They're a function. An agent is a policy, which is a function from state to action. Takes a state and says, go up. And then you can ask two types of questions. You can ask local questions, or why did you step up? And you can ask global questions, or what is the target? Where is this car going? Why is the Pac-Man going? How is it going to grab? How is it going to escape ghosts and so forth? And what we argue is, so we're going to target the last one, the global types of queries. We argue that humans ask global questions. They don't look for local things, and they want global explanations. A second thing we do is we're not going to produce explanations for the agent. Basically, what we're doing is going to describe how the agent is performing. So we have an assumption here that by observing the agent interacting in the environment, the user is going to do this mental jump and understand how the agent is, trust the agent or understand how the agent is performing only by viewing how it's interacting in the environment. So the way we go about this is we again train this agent, assume that somebody trained this agent, and let it run in the plan. So it produces action, gets states, and so forth. And we do this for a long time, and this gives us a lot of clips of this agent playing around the environment. As you can see, a lot of clips of. I forgot his name. So our user here, Homer, is looking at these clips and supposed to understand this agent. And the main question is somebody saying that in the chat. Bender, thank you. Bender is the name of this robot. So the main challenge here is that Homer or any user has a very short attention span. So you need to select which clips to show. And you have only like a handful of clips that you can show the user. So these should be critical clips to understand how the agent is behaving. Previously, the way this challenge was addressed, so I cite here works by my co-authors, and again, sorry if I don't cite your work. So basically, it was based on heuristics. In highlights, for example, what Ofa and her brother did was identify a heuristic to measure the importance of states. And then they produced clips in which there were states with high importance, basically highlights of clips. The problem with previous approaches was, first of all, that it was heuristic, and second of all, it was very static. And what we want is something interactive. We want our users to ask us the clips that they want to see. And this is a trailer to, I guess, to the this is a trailer to tomorrow for the queries on the clips that it wants to see. And then we want this to be like an interview, right? The user is using our tool to interview the agent. He wants to see, produces a query of what it wants to see, gets some clips, updates the query, and so forth, like an interview. A big challenge of this is that so inherently an inherent challenge of this paradigm is that we need the users to express queries. We want them to say which clips they want to see. So and specifying properties of clips is a challenging task, right? A clip is something that proceeds over time. How do you say what you want to see? Right, your query should be something that talks about time. And moreover, we want this. We want to aim at laymen. We want users with no formal training in anything. They don't know anything about reinforcement learning. They don't know anything about logic. Anything. Okay, so this is where I step in. So I'm going to talk about an LTL. So I come from, as I said, I come from a field that's called formal methods or formal verification. A key point in historically, a key point in our field is 1977, where Amir produced a logic called LTL, which is short for linear temporal logic. It's a logic for reasoning about infinite computations. In verification, basically use LTL to describe correct behaviors of systems. Basically, it says it's a way to express properties of like which infinite computations I'm interested in. This is an extremely influential paper. Amir Pnueli won the Turing Award for this paper, and it basically opened up this field. We're not interested in infinite computations. Rather, we're interested in finite computations. We want finite clips. We want the users to query finite clips that they're interested in. And so we're going to use LTLF, which is LTL on finite traces, introduced by Giacomo and Vardi quite recently. So this is going to be a crash course on LTLF. As a running example, consider this setting, which we use in our experiments. Here we're training an agent. We trained an agent to control the green car, and it's running in this highway. For us, a clip is basically a sequence of states. The car, so there is a proposition that says which lane the car is on. So here, lane 4 would be turned on, and lane 1 would be turned off. Here, there is a car behind the green car, so behind would be turned on, but above or below would be turned off, and so forth. So these are the propositions, and that's a state. And then you can query these kinds of states. So here is an LTLF formula that says X is read next. So next behind means that I'm looking for clips in which in the next time step, in time step 1, the green car is behind some blue car. F is read eventually. Eventually lane 1 means that I am interested in clips in which eventually the green car is positioned on lane 1. For example, this clip was obtained by calling the query eventually lane 4. The green car is eventually on lane 4. G is read always. So always slow means clips in which the green car is always driving slowly. Until, so lane 1 until above means that we want clips in which the green car is on lane 1 until at some point it's above some other blue car. So these are the basic temporal operators, and then you can make all kinds of combinations, which I won't get into. So I'll now describe how we implemented our backend. As I said, we run this agent with a plant, and this produces a library of clips. We concatenate them to produce one long computation. And then our user comes in and produces an LTLF formula phi. The first thing that we do is add an eventually operator in front of it, which means that we're looking for clips that end in a suffix that satisfy the user's query. For example, he would say always slow. So this is a long clip that ends in a suffix that satisfies always slow. And then what we do is we use the automata theoretic approach to reasoning about LTL. This is a very deep approach. There's a lot of papers about it, and I won't get into it. Please feel free to ask me offline. I point to a tool that we use by Fugiti that translates the formula eventually phi to a DFA, a deterministic finite automaton, A eventually phi, which accepts words that satisfy eventually phi. So this automaton accepts all the words that the user cares about. And then what we do is run the library, the word that we collected on this automaton, and look for a position that accepts, that points to a clip that enters the user's query. So if you lost me, the take-home message from this is that using this approach, we make only two. So for using this approach, we make, for each query, we make at most 2 passes on the library. And once you get this DFA, once you run their tool and get a DFA, this is super fast. Answering queries, processing queries is super fast. The bottleneck is producing the clips, as can somewhat be expected. Okay, so another challenge is that, recall that I said that we want to get formal descriptions of clips from laymen, and the highlight is on the layman. So we don't expect our users to have any formal education in RL and not in logic. So we can't expect them to know LTL, and we don't want to teach them LTLF. And so we need some sort of simplified user interface. And this is a screenshot of our user interface for Frogger. The user interface goes as follows. There is a description of the start state. So a user, without knowing, so what this user interface does is, without knowing, the users are going to write LTLF formulas. The first thing they do is describe the initial state. So which propositions hold in the initial state, same for the end state. And then they have some temporal constraint. For example, here, we want the Frogger to press down at some point. So when we click submit on this query, we get, this is one clip that we get. Oh, sorry. This is one clip that we get. Here, let it run. As you see, the Frogger starts before the road, it ends in the river. And if you saw at the last point, it took a step down. So it satisfied this query. Here's another clip, again, before the road, going up, makes a lot of down moves, and reaches the river. So these are 2 clips that satisfy the user's query. We ran a user study to see, well, we asked basically usability questions. So can laymen understand this? Can they form LTLF queries? Do they understand this connection between the interface and the clips that it returns? Basically, do they understand LTLF? Can they form queries, and is the tool expressive enough? Can it express the queries that they're interested in? Without getting into all the tables and so forth, take-home message is yes, there is a learning curve. It's not too, it takes I don't want to lie, but 10 or 20 minutes before they understand it. But overall, they were happy about it, and they passed our tests for understanding our tool. I will sum up with future work. So the next thing that we're currently doing, this is current work rather than future work, we're trying to show effectiveness of our tool. Does this tool help users understand agents? By selecting clips that they find interesting. The next thing on in the horizon is to look at develop a richer tool, so a richer query language. For example, our users were asking to express aspects of the environment. If you recall, so as an example of this, recall the highway clip I showed you. You can say things like, I want to see how the user acts in a traffic jam. So traffic jam is a property of the environment, and it can't be expressed. Currently, it can't be expressed using our tool. A second thing, which also came up in the question session in the previous talk, is quantitative aspects. So I showed you 2 clips of the Frogger, one in which it stepped down on once, and one in which it stepped down a lot of times. Maybe you have a preference towards one of them and not towards the other. Maybe you want to see, a lot of down clicks. So let me stress. So I'll just stress out that in both of them, it's not enough to only define the language. You have to, do the whole process. You have to rewrite the interface, think about which automaton you need. You need to re-implement the backend. All of these are not trivial at all. And finally, so in the longer run, we want to look at more connections with formal methods. We want to, one thing that we want to do is talk about explanations instead of descriptions. And that's it. Thank you for your attention.
Thanks a lot for your presentation. It's really good. Also, all the images, and it was fun. It was easy to follow. So do we have any question? Yes. So we have two questions. Gabrielle, can you please?
Yes, thank you. Very interesting presentation. Thank you.
Thank you.
Basically, two aspects that I did not fully get. Like the first one is, it seems like that if you say you run the library through the DFA, it means like one clip by a clip until you found a positive answer. And the second thing is like, for this purpose, your clips must be formally like somehow tagged, like what happens after what, what's the source for this data? Like, where does it come from?
So what we do is basically, so it's a very technical question. So what we need to do is take a state of the simulator, and we need to map it to a state. So a state is basically which propositions hold it. It's a set of propositions that hold in each time. And then yes, we concatenate. So we run this agent on the environment, collect this sequence of you can do so. If you think about it theoretically, you can do this once. You just run the agent on the plant and in the environment, and just collect a long sequence of states. Forget that it comes from a simulator, just a sequence of states. And then yes, we run. And then what the automaton theoretic approach does is run the automaton on. You think of this as a word. The automaton reads states, and it accepts only when the prefix it read so far and contains a suffix that answers the user's query. It's very deep. I skimmed over it.
Okay,
but this is more convincing.
Your clips kind of fall out of the application, like it's just the sequence of states of a run in the actual plant.
Right, and then so once you find it, you need to. So what you need to do is translate it back somehow. You need to say, so this state came from the screenshot. You need to basically make the movie, right? You need to take the state and turn it back into a screenshot and concatenate these screenshots back together and show that to the user. That's exactly what the tool does.
Okay, thank you.
Okay, so we have another question from Benjamin.
Hi, Guy.
Hi.
Great talk. Thank you for that. I have a couple of questions because it was a very good talk, but I'll stick to one because of time. So maybe we can talk on the Slack or something after. But so, one of the benefits of LTL is that you can get very descriptive with the constraints. However, I can imagine that when it comes to a layman trying to specify these constraints, they might not be descriptive enough. And I would assume that there would be many different clips that satisfy one LTL constraint, for example. Is that something that can happen? Have you thought about summarizing those clips, for example, or anything in the direction of that?
Yes to all. Yes to all. Yes, we get a lot of clips. We get for simple queries, you can get to the hundreds, I guess. And this is, I think this is exactly what the quantitative aspects in this last slide is pointing at. How do you prefer, how do you give a preference over these clips? Yes, this is definitely something we're thinking about. Like, do you prefer long clips? Do you prefer short clips and so forth? So, okay, let me answer again. If you give a very simple query, for example, you don't constrain anything, you can get like 1,000 clips and you just have to scroll through them. But if you give a very precise query, you would get a handful, 10 clips, and then you could just go over them.
Yeah.
So yeah, it's all future work. So how to, I think it's extremely interesting how to change the order between the clips that you see.
Yeah, I agree. I mean, I think that in an iterative method, potentially users could specify their LTL constraints more until they reach a clip that they're satisfied with, or something along those lines.
Yeah, sure. And
I wonder
in this tool,
from your experience of using it, how often do you get to the point where you've reached a clip that you're truly satisfied with, for example?
Yeah, you do. I mean, it's exactly the process that you're describing. You feed in a query, some LTL formula, and then you see clips and say, okay, that's not exactly what I wanted. You change it, and at some point you hopefully you see what you were looking for.
Great, thank you, Guy.
Sure.
So thanks. If you have any other question, I will also add some question on the Slack so that we can continue discuss this paper. So yes, I will now introduce the next paper that is why not this multi-agent pathfinding plan instead, and it's contrastive map-based explanation for optimal multi-agent path finding. And this paper is from Martin Brandau and Jonathan Sentiawan. I hope I pronounce it correctly. Martin, yes. Thanks a lot. Can you hear very, like the volume, it's low for me.
No.
Still kind of low, but maybe it's on my side.
Maybe now, is it better now?
Yes, still low, but it's fine. It's fine. We can hear you just a bit low.
Okay. All right, thanks for the introduction. So this paper was done together with Jonathan, who is an undergraduate student who was working together with me on this. The motivation for this work is on multi-agent pathfinding. So we recently published a paper in AIMAS where we were talking about so basically users of multi-agent pathfinding methods, such as people working, researchers working on warehouse automation, or engineers working on warehouse automation, also computer games. And we've seen that we were trying to talk to them to understand what kind of uses could explanations have. And it turned out that many of them were excited about the use of explanations to solve some of the problems they have. And one of them is that it's very difficult to understand these MAPF plans. And the other one is that it's very difficult to tune the behavior because these are typically very large environments and many agents, and it's very difficult to tune, for example, the cost functions that or the maps that lead to the behavior that you want. And so out of that paper, some insights that came was that MAPF explanations, according to these expert users, could potentially be helpful for developers to tune cost functions, for warehouse or game designers to improve the maps, and to understand and predict planner behavior, or even on-site warehouse engineers to tune behavior on the fly. So in this paper, we want to go one step in this direction for optimal MAPF, which is to try and answer questions of the type, why is the plan equal to X, not Y? So this was also something we have seen in people working in warehouse automation. For example, they typically have an idea of what the path should have been, but they want to know why it was not. And so we're in this paper, we look at map-based explanations, which means that explanations that answer this. The plan was X, not Y, because there are no obstacles in cell C, for example. So it grounds the explanation on the map. We focus on this because it is useful to warehouse and game map designers, and because of some previous methods we've been working on for single agents, where the user study results suggested this was useful also to improve user understanding of the single agent problem. So in this specific level, the contributions are to formulate two kinds of explanation problems, very related to each other, and then propose a benchmark and the methods and evaluate them. So the kind of informal definition of the problem is this. So we want we call it a full MAPF map-based explanation problem, which is given the graph and your map, and which is shown here. You have some original plan, but there was a plan that you expected. And so the user can provide this plan and ask, why was the plan not this that I expected? Why is it the original plan and not this one that I expected? And then the goal is to find the minimum amount of changes to the obstacles. So for example, obstacles that you can add to the map, so that in this map, the plan that you were expecting is actually optimal. So then you could, the explanation would sound something like this. Well, the path is not what you expected because this area here is free. But if it was occupied, then the optimal path would be what you expected. Right, and then there's also another problem. So in this first problem, you give a full MAPF plan with all the agents, and in the partial plan problem, you can ask about specific agents. So for example, why doesn't agent 1 do this path? And you don't care about the other agents can do something completely different. You don't care. You only care about reasons for why this specific agent or subset of agents did not take the path you expected. And so in the paper, we propose 3 different methods. There's a search-based method, which is complete and optimal. Basically, it's breadth first search, where each state is a vector of the obstacle changes that you're going to add to the environment. And then each neighbor of this state adds one extra obstacle and an extra obstacle. And you only add obstacles to locations that can change the optimal solution, so cells along the optimal path, and also cells that do not intersect with your desired plan. So you can stop once your plan is optimal in G, in the new map. Unless, of course, what you're asking is impossible, and then you stop when you exhaust the space. And then another method that we introduced was an incremental optimization-based method, which is basically an extension of a previous method we introduced last year at ICAPS for single agents, extended to MAPF. Here, the main idea is that you incrementally build a set of bad MAPF plans, which should be made infeasible. So in the beginning, you have no such plans, and you compute what is the current optimal plan for our map. And if this plan is already what you were expecting, then you can stop. If not, you add this plan to your set of bad plans. And then what you do is you find a new map that will make all these plans that belong to B infeasible. And then you keep doing this over and over again. And at some point, you'll have a lot of plans that are basically lower cost than the one you wanted, and all of them will become infeasible, and yours will become optimal. This is optimal for the full problem, but this is not complete for the partial problems, because these plans in B are full MAPF problems. So it's not complete for the partial case. And then we also introduced another method, which is a kind of a baseline, a simple baseline. So in single agent inverse shortest path, but what you do is you try to find the new edge weights such that the single agent path becomes optimal. And in joint ISP, you basically treat the path of each agent of your MAPF plan separately, ignoring the other agents. And you want to make each of these paths become optimal in the path, in the map, in the new map, while ignoring other agents. So you want to find a map that is common to all agents, and for all the agents, the paths that you want to become optimal in that plan. Of course, this is not complete both in full or partial problems, but it might be interesting as a baseline, and also because adds this extra constraint that all the map is basically good for all agents, and they don't interact with each other. It might be interesting for future user studies, even though we don't look into that. So then our benchmarks to generate them, we gathered many 8x8 MAPF problems. We computed the optimal plans, and then basically we picked 2 random agents and waypoints to generate a set of 100 problems, like random problems, where you have an original plan and map, and you have a question, which is basically 2 agents and different paths, and you're asking why isn't that these 2 agents didn't move like this. So here's some examples of what these explanations look like. I also showed it in the beginning. So you have a plan, MAPF plan. Each of these agents, I think they start in the squares and end in the circles. And then in this case, I asked, why didn't agent 2 do this and agent 3 do this trajectory here? And then the explanation, the algorithm finds that by adding an obstacle here, these 2 paths become optimal. So it says, well, because the cells in purple are free, but if they had been occupied, then your plan would have been optimal. And well, this is a similar one as well. Sometimes, so our explanations try to make it, so we'll give you an explanation head that has the least amount of changes to the map. In this specific case, you have to make 2 changes to the map in order to get your desired plan. Then we have results on a lot of, so these 100 problems, and we show this incremental method. So in the full problems, the incremental method is optimal, and it is faster on average than the search method. And in partial problems, basically each method has problem solving problems generated specific subsets of problems, and so each method kind of has its own advantages and disadvantages. And but basically one interesting thing is that this incremental method is orders of magnitude faster than the search-based method, even though it's not complete. So it could be a good, if we don't care too much about the optimality of the explanation length, we could use this suboptimal method because it's much faster. So to conclude, we introduced this idea of map-based explanations for MAPF. So this is about asking why isn't the MAPF plan this one, or why didn't this subset of agents take these paths instead, and answering with properties about the map that will have to change for that plan to be the way you expect it. We propose 3 methods: a slow search method, a fast incremental method, and a baseline that is not optimal but might be interesting because all the agents are conflict-free in this explanation. So future work, I think, is trying to understand whether users would find these explanations more intuitive, for example, these joint ISP ones, and then actually going back to our initial expert users working in warehouse automation and computer game development to see if they actually find this useful in on the ground. So thanks a lot for your attention.
Thanks for your presentation, Martin. Do we have any question? Yeah, we have one question from Michael. Michael, yes, you have a few minutes. Please go ahead.
So just a simple question. Is this problem hard, computationally hard? Finding like a change to the map that makes it make this plan optimal?
So for the when you want a specific, the full MAPF plan, so when you give the paths of all the agents and you want to find the changes to the map so that you get this specific completely specified paths of all your agents, that's quite quick, but it's really computationally hard if you only specify part of the agents, because
you have a proof in the paper?
No,
I can read it?
no.
Okay.
No.
Sorry.
It's all, yeah, no. it's all informal. But when you have when you only specify one or two agents, then it's very difficult to compute, because when you each change that you make in the map, there are many solutions that satisfy these agents that going in this direction. That so you specify agent paths, and there are many solutions of maps and of paths for the other agents as well. And so it's very difficult to find there's so many combinations of maps and paths for the other trajectories, and you have to go back and forth between the two. So yeah, but sorry, no formal proofs or anything.
I mean, you do have two numbers, right? Like the optimal and the one that you need to make optimal, right? And I guess the costs are integers, so you would have to make a particular changes that will increase the cost of the optimal plan, of an optimal plan, right?
Yeah.
And among those, you actually, I mean, there are not too many, right? Yeah.
In the partial case, you do not provide a full plan. You provide a constraint on the MAPF plan, because you're saying that I want a map. So any MAPF plan in which these two agents have these paths, but all the other agents can do any path. So I want to find the minimal changes to the map. So that's the problem constrained in this way. So
yeah, I guess the check for optimality is already hard, right? Once you change the map, I guess the check for optimality is hard. Yeah, thank you.
Okay, so we have another question from David. Please go ahead.
Yeah, I would think that in a lot of cases, the reason that the user's plan would be non-optimal would be because of conflicts between the agents, not necessarily the presence or absence of fixed obstacles. Can you comment on that and what you would do in that case?
So I think from my understanding is that you're concerned about the usefulness of this specific kind of explanation, right? I think we did some user studies last year, and what we found out is that this is useful when you're, for example, imagine you're designing a computer game, right? And you want to know why isn't that these agents are not moving this way that they expected, and tracing having a reason based on the map tells you that there's something wrong with the map, or if that's the behavior you wanted, then you will have to change something about the map. In computer games, this would be something like, well, these areas here are currently too high cost, or actually for that to be optimal, I think you have the wrong assumptions, because I don't know, there's an edge missing here, or there's an obstacle that should be here. In the case of warehouse, I think this is useful for there is such a job as layout designers who decide where to put the packing stations and etc. And a small change to this problem, that in this specific problem we're adding obstacles. In the warehouse case, maybe we would be moving an obstacle from one place to the other, or things like this. Because you can design, for example, where the pillars of your warehouse are. Maybe you can, or maybe you can design where the shelves are put, and then this influences something about behavior.
Right, but even
in computer games,
even in this case, I would think that somebody who is doing a design would be trying out problems and would say, you know, why didn't you use this plan instead of this other plan? And in fact, the reason is that you chose your particular plan because it causes fewer conflicts and fewer weights, right? Because of conflicts with other agents, and in that case, I would expect that the explanation that you would need to give to the user to get them to move on would be something to the effect of, you know, if this other agent weren't present, then your plan would be optimal, right? Or
yeah, I agree. There are many possible So if you want to find reasons for why a plan is not the way you expected, there could be, it could be because of another agent, but it could also be like changes to the environment could also lead to that behavior we're expecting. And so it all depends on what the user wants, right? If the user only wants to understand the how agents interact and influence each other, then your kind of explanation is useful to them. If they're interested in tuning the cost function that they use in order to obtain desired behavior, then we would need yet another kind of explanation that would tell you, well, because your cost function is like this, but if you change this hyperparameter or this weight in your cost function, then that will. And then yet another user is the user who's designing maps, and there are such users. So our explanation was targeted at that specific kind of user. But of course, there are many. There are also explanations based on agent conflicts and cost functions and many other things like event triggers. And if you're interested in that, our AMAS paper, it has a lot of different kinds of explanations that were raised by these people in warehouses and computer games. But thanks for your.
Okay, thanks a lot. Sorry, we will have to move further question to the Slack channel. We had planned 10 minutes break, but we are a bit over time. If you want, we can continue and have the break after the second session of the papers, or take a break now. I don't know. We are already a bit late, so depends by you. Myself, I would be happy also to continue with the second session. Anyone? Any preference? Yes, okay.
Yeah, I think we'll have to just carry on through.
Yes, I think it's better. So I give the word to Alan, which will lead the next section of papers. Thanks a lot.
Thanks, Sylvia. Okay, so the first talk in the second session is explaining soft goal conflicts through constraint relaxation. And is Rebecca, are you doing the talk? Thanks.
Okay. I hope you can see my slides.
Yes.
Okay, then welcome together. I'm Rebecca, and today I would like to present joint work with Jeremy Frank and Jörg Hoffmann. So imagine you are a NASA researcher and have to schedule the next Mars rover mission given a set of data points that should be collected. But unfortunately, it's not possible to collect all of them, and now you have to find a trade-off that satisfies you and your colleagues. In this setting, explanations which would help you to find a good trade-off would be really useful. So in previous work, we introduced a framework which uses plan properties and their dependencies to provide such explanation. In this framework, then you could, for example, ask, why is this X-ray image not included in the plan? And then the framework would tell you which of the currently satisfied soft goals, or in our case, data points, are in conflict with the X-ray image. Now, this explanation, as proven by a user study, can already be helpful to find better trade-offs, but what they don't do is to explain why this conflict exists at all. And in this work here, we want to address this question by the underlying constraints of the planning task. More precisely, resource and time window constraints. So in our example here, we have a limited resource for the rover and a time window for the data upload to the relay satellite. And then, given the constraints and the conflict, a natural way of explaining why the conflict exists is by relaxing the constraints until the conflict disappears. And then we can use the amount of relaxation we needed as an explanation for the conflict. In this paper, we used a resource, the planning with resources where we have a fixed initial amount of resource for the fixed amount of resource at the beginning. Then each action can consume a certain amount of this resource. So here, for example, driving costs 2 units, and we don't allow refueling. So we only have a resource consumption. And then given the setup, the relaxation of a resource would basically be, could be to simply increase the initial amount of resource available. And for time windows, or for time in general, we restricted ourselves to a notion of time that can be compiled into classical planning, where we have a set of action that is restricted by a given time window that is defined by an opening and a closing time. And in our example here, the uploading then is only possible when the current time value is between the opening and the closing time, and each action additionally has an execution time, which is added on top of the time when it's executed. And given this definition of time windows, relaxing a time window can be done by either decreasing the initial, the opening time, or by increasing the closing time. And then you get this sort of partial ordering for the relaxed tasks based on time window constraints. Now, given such a set of relaxed tasks, what we want to use for the explanation is the minimal relaxed task under which the conflict disappears. So if we, for example, have this case here, where it's still not possible to take both soil samples if you have 6 units of energy, but with 7 it's possible, then that's the relaxation we are looking for. And for time window constraints, it's basically the same procedure. Given this partial ordering, we might get more than one minimal relaxation. And then overall, we explain why it's not possible to take the soil sample and the X-ray image at the same time by telling the user that this would be possible if you had 2 additional units of energy, or your time window would start 2 units earlier or 1 unit later. Okay, but how do we compute these minimal relaxations? What we do is we compute the conflicts for each of the given relaxed tasks, and then check when the particular conflict disappears. And to compute the conflict for each task, we use build on an algorithm we introduced in previous work, which, given a task and a set of soft goals, can compute the minimal unsolvable goal subsets, which are basically the conflicts we are talking about, via the maximal solvable ones. And that is done by basically an exhaustive state space search, where you explore the search space in a depth-first search manner, and on the way you track the maximal solvable soft goal subsets you find. And to reduce the search space, we also use a pruning function which prunes states from which no superset of the already reached solvable subgoals is relaxed reachable. And then after exploring the whole reachable search space, we have our maximal solvable goal subsets we can then use to compute the conflicts. Now, given this algorithm, the most basic idea to use it to compute the conflicts for a given set of relaxed tasks is to call it separately for each task. But you can do better. Because, for example, all maximal solvable goal subsets reachable with 5 units of energy are also reachable with 6. So instead of having a cold start basically for the pruning function every time, you could instead propagate the maximal solvable goal subsets of less relaxed tasks and use them to initialize the pruning function. In that way, you get over time a more and more powerful pruning function. And then this one other bottleneck is that you basically generate very similar search spaces over and over again, because the search space of more relaxed tasks is more or less a superset of the one of less relaxed tasks. So instead of generating one search space for each task, it could be beneficial to reuse the search space and just expand it. To do that, we start from the least relaxed task, again expand it, but this time you cannot use the pruning function based on the current task, because otherwise you might prune states that are later reachable, but instead you have to use the maximal relaxed task, which then in the end leads to weaker pruning function. So there is a certain trade-off between reusing the search space. And then after exploring, while exploring the search space for the current task, we collect all states that could be reachable in more relaxed tasks, but are currently not. And then for more relaxed tasks, we use these states to continue our search instead of generating the whole search space over again. We implemented these two algorithms in fast downward and ran experiments on 4 resource and 3 time constraint domains. And here we have the coverage results where an instance counts as solved if it was if the conflicts for all given relaxed tasks could be solved, could be found. Here the baseline is just calling the introduced algorithm separately for each task without any knowledge propagation. Then ICR is with the propagation of the maximal solvable goal subsets for the pruning function. And in SSR, we reuse the search space. And then we get the following results. And the 2 most interesting results here are, first of all, that propagating the maximal solvable goal subsets is always beneficial. So it always increases the coverage and never decreases it. And that ICR and SSR are complementary. So ICR is better suited for resources and SSR better for time. This could depend on one hand on the pruning function, and on the other hand, that for time constraint relaxations, so increasing the time window by 1 unit only adds a few additional reachable states, while increasing the initial resource amount can add more additional states. And this is advantageous for SSR because it only adds the newly reachable states. So to conclude, we introduced minimal constraint relaxations as a way of explaining why conflicts exist and how they can be resolved. And we, to compute them, we introduced 2 algorithms that are complementary for resource and time window constraints. And our future work is to incorporate these explanations in our online iterative planning tool, and to then conduct user study to evaluate the impact of these new explanations on the performance of finding good trade-offs for a given set of soft goals. Thanks a lot for your attention. Are there any questions?
Thanks, Rebecca. Okay, David, go for it.
So there's a dual here between increasing the amount of a resource available and relaxing the actual precondition that requires a certain amount of the resource. So for drive, for example, you could consider relaxing the precondition that says that you've got to have at least this amount of energy. I'm wondering if those 2 are equivalent, first question. And then the second question is, If you could, in a case where energy, for example, was a continuous quantity rather than a discrete quantity, that you could take that precondition and drop it and see that the problem is now solvable, and then take that precondition and actually solve for the value that you would need as a bound in order to make the problem solvable.
Yeah, that are both great suggestions. So yes, decreasing the cost of driving would be equivalent to increasing the initial amount if we only have to use this particular drive action once, which, I mean, is not in general the case, but if that's the case, then they are equivalent. But of course, there are other ways of relaxing resources we didn't consider. Also for time windows, you might decrease the execution time, but then this partial ordering for relaxed tasks gets much more complicated. And then, yes, so relaxing a task by removing preconditions would be an option, and is supported by our implementation basically. So it doesn't really care about what the original relaxation is. What you then suggested to then reintroduce the variable in case that's really the reason for the conflict, and then like try to figure out to what extent we need to increase it to still be able to collect both data samples. Yeah, that would be a nice way of like finding the minimal relaxation for a particular conflict. What we currently do is we compute all minimal relaxations for all possible conflicts before user interaction, basically, such that we can answer all possibly occurring questions. But for like an online version of our algorithm, what you suggested would probably be beneficial.
We've just got, sorry, can I move on to just a quick question from Michael Katz, and then any other questions, please just flag, please.
Okay, thanks, great work. So I don't know about the time windows, but the resources can be, it's just mapped into costs, right? Additional cost functions. What do these relaxations look like at the cost level, right? What do they actually mean? And have you considered something like that? There was also previous work by Houghton Lacoste and York and other collaborators on resource constraint planning, which is also, I guess, the same setting, right?
Yes. So you mean instead of like using a concrete resource variable, you use the action costs to represent them.
Which is encoded as action costs, as additional cost function, right?
Yeah, in general, that should be possible. I'm not aware of any work that then actually like has this relaxation order around the cost function.
Right. So that's what I want to figure out, right? So what is the equivalent of doing such relaxations on the cost functions, right? Like it's kind of
It should be equivalent if you have one cost function that encodes the resource. For right now, I don't see any issues. For the time windows, it's a different question, but for the resource, I think it should be possible.
So it's basically something that you could just put into a planner, like that supports multiple cost functions. And
yeah, I mean, you still have this underlying computation of the constraints, which is not like just requesting a plan. So there's some additional adaptations necessary in the planners for that use the action cost.
Great. So can we move this discussion onto Slack and move on to the next talk, please? Thanks, Rebecca. So the next talk is Discrete Time Series Clustering and Delineation, a tree-based approach to linear temporal logic discovery. And is Brennan going to do the talk? Great.
Everybody see my screen?
We can see your screen, yeah.
Okay, so hi everyone, my name is Brennan Cruz, and today on behalf of myself and Dr. Christian Muse, I will be presenting our paper titled Discrete Time Series Clustering and Delineation, a tree-based approach to linear temporal logic discovery. So time series data is everywhere, from athletic activity monitoring to weather recordings to financial transactions and even pandemic severity logs. The relevance of time series data analytics is more important than ever in this technology-driven world. So the paper that I will present today is designed to advance this cause and strengthen the ability of researchers to learn from the past and improve the future. But first, we need to dive into a few underlying concepts. And the first is linear temporal logic, or LTL for short. So LTL is a modal logic that was first proposed by Bernoulli in 1977, and it's a powerful language that allows us to encode relationships between events in time. And the language consists of two fundamental operators, next and until. And from those fundamental operators, we can also arbitrarily introduce additional operators for syntactic simplicity. And as an example of LTL in action, we can represent the characteristic of a traffic light that always turns red after yellow as globally not yellow or in the next state red. And the next concept that we need to look at is trace data, because traces represent the input to our problem. And traces can simply be described as a representation of time series data that's designed to record changing states of the world. So denoted as a series of bit vectors, fluents within traces are either active or inactive at various time steps, which allow us to study the interaction of elements within a domain. Next, contrastive explanations tie traces and linear temporal logic together by describing temporal differences between two sets of planned traces, where the goal is to identify temporal specifications that one set of traces entails, but the other does not. So if we incorporate a slightly different traffic light cycle into our example, where the light also turns yellow after red and before green, we can see that an effective contrastive explanation between these two unique systems could be globally not red or in the next state green, where one of these systems satisfies the LTL specification, but the other system does not. So looking at some prior work in the area of automatically generating contrastive explanations, we observed two dominant strategies that have been adopted by researchers, where the first is SAT-based methods. So the idea is that by formulating the problem into propositional Boolean logic, it can simply be fed into a SAT solver to establish temporal specifications. These SAT-based methods, however, they can be susceptible to failure when sets contain imperfect traces. So to combat this in 2019, Kim et al. Introduced a Bayesian inference method called Bayes LTL that allows specifications to be inferred through a probabilistic approach. And this also allows contrastive explanation generation to be more robust to noisy input. And since we're modifying Bayes' theorem through this approach, a user's preferences can also be incorporated into the prior function of Bayes' theorem. So what exactly is it that we do? So our paper represents two primary contributions that expand the scope and capabilities of contrastive explanations. And our first contribution is the expansion of contrastive explanations to incorporate multiple sets of traces. So all prior works accept exactly two sets of traces to contrast. However, our approach accepts K sets, which can be defined by the user. Additionally, prior works require that these two sets of planned traces be previously differentiated into positively and negatively labeled sets. Whereas we formulate this as an unsupervised clustering problem to automatically identify which groups of traces to contrast. So more simply, we essentially have a big bag of unordered and unstructured traces originating from K unique systems, and our approach clusters these traces into distinct segments of behavior and describes the differences between these unique systems through contrastive linear temporal logic specifications. As a starting point for our problem, however, we needed an evaluation data set to implement and measure our approach. And to do this, we embraced 6 domains from the International Planning Competition, along with 3 unique vocabulary sizes. We then fed this into individually into a diverse planner bounded by stability similarity to generate 100 plans for each domain with a maximum of 25 identical actions amongst plans. And this provided us with 18 unique data sets to probe various aspects of testing. We then implemented our tree-based clustering method to convert raw trace data into delineated subsets. And the first step in our approach was to establish a splitting process that allows two balanced subsets to be created from a larger set of traces via contrastive linear temporal logic specifications. Next, we initialize our input set of traces into a root node of a decision tree, and we recurse our node splitting process until desired quantity of leaf nodes are discovered, which represent clusters. And then finally, by simply reading the linear temporal logic specifications off of the branches of the discovered tree and using conjunction to establish formulas via the path of root to leaf, we derive definitions for each cluster. So looking deeper into our node splitting process, we use a cyclical Monte Carlo technique to split a given set of traces into two balanced subsets using contrastive LTL. And our process begins by randomly sampling two balanced subsets from the parent set of traces. And we use the Bayes LTL framework to discover candidate LTL formula to differentiate these subsets. We then evaluate the information gain that's achieved by the candidate LTL, which is a metric which we define to measure how equal in size the resulting subsets would be using that LTL specification to split the parent set of traces. And then retaining the LTL specification that maximizes information gain, we repeat this cyclical process until either a maximum iterations parameter is reached or a minimal information gain threshold is met. And recursing this node splitting process in order of node size, we arrive at generated trees, such as the example on this slide from the blocks world domain. And looking at the node circled in yellow as an example, we can see that this cluster is defined by not entailing the root node's LTL, but successfully entailing the LTL of the next two nodes along the path of root to leaf. And the definition of this cluster then becomes the conjunction of the three formulas, which allows it to be perfectly differentiated from the 7 other clusters. Next, in order to evaluate the strength of our tree generation technique, we then generated 20 trees from each domain and vocabulary size configuration, and we measured the average depth and LTL size distribution of these resulting trees. And average depth is an important metric for us to look at because trees with lesser average depths are indicative of higher quality LTL since they contain more efficient splits. And for reference, a perfect tree of 100 traces would have an average depth of approximately 5.76. And as you can see in the table on the right of the slide, each domain and vocabulary size configuration that we evaluated have average depths representing sizes that aren't too far off of this amount. And then average LTL size is also an important characteristic to evaluate, since smaller LTL sizes may be indicative of overfitting, whereas larger sizes may represent overfitting. And to measure LTL size, we simply counted the quantity of unique subformulas within a given LTL specification. And then again, referring to the table on the right, we can observe a very reasonable LTL size for each of our domain with no extreme values standing out, which represents a likely robust fit for the LTL discovered within our sample domains. We then conducted a variety of experiments to test some different elements of our approach. And we were first interested in analyzing the scalability of our approach by measuring the relationship between node size and splitting time. So to do so, we conducted 10 splits for each node size of randomly sampled traces in increments of 10 from 10 to 100. And we observed a near linear positive relationship, meaning that larger node sizes corresponded with greater execution times. So this highlighted the importance of our sampling step, because with larger data sets, this will grow continuously large. And sampling is a very important step to minimize this complexity. So this observation also intrigued us to then evaluate the effectiveness of our sampling step, because to minimize complexity, the smallest possible sample should be taken. So we estimated the probability distribution of information gain based on sample size by running 100 splits of sample proportions of 2%, 5%, 10, 40, 70, and 100%, and evaluating information gain based on those splits. And as would be expected, higher sample proportions tended to provide greater representative ability. However, the size of this effect was interestingly small scale. So as you can see in these kernel density estimations for our evaluation domains on the slide in front of you, samples as small as 2% were effective in some domains, but samples as small as 10% in all of our sample domains. So this certainly represents a very strong opportunity for runtime savings. The next area that we looked at within our approach was the impact of the maximum iterations parameter within our Monte Carlo splitting procedure. And to do so, we conducted 20 splits for each iteration value in increments of 5, from 5 to 50, recording execution time and information gain. And here we observed a diminishing marginal increase in information gain with a linear increase in time. So this means that although the cost of additional iterations is constant, the probability that a better LTL specification will be found decreases with additional iterations. And we also see that these information gain curves really start to flatten out. And we believe that this is because LTL satisfying the information gain threshold does not always exist. So our algorithm currently only stops early if the information gain threshold is reached. So if it's impossible to reach that threshold, then all iterations will still be conducted, even if the optimal specification has already been found. And this leads us to our final experiment, which also pairs highly with future work. And the idea here is that if an intelligent splitting process could be identified that allows future splits to learn from previous splits, then the efficiency and scalability of tree generation could be drastically improved. So as a preliminary attempt at facilitating intelligent splits, we tested a process where instead of resampling subsets from the parent set, we used the candidate LTL to establish 2 new subsets. And then we rebalanced the subsets by randomly shifting traces from the majority set into the minority set. And then we reran Bayes LTL on these new subsets with the goal that the new LTL would be discovered and the sizes of these resulting subsets would then converge. So this attempt that we made, we found that the same LTL tended to be repeatedly discovered, so no learning was observed to occur. But this was a key step for us to infer that within future work, greater freedom is likely necessary for the initial allocation of traces, and future work should really focus on the strategic introduction of variants to better facilitate learning. So in summary, within this paper, we introduced a novel clustering and delineation method that uses a decision tree approach to expand contrastive explanations to case sets of traces, in addition to allowing these clusters to be automatically identified in an unsupervised fashion. And we hope that by introducing this novel framework, we'll empower researchers to view and understand time series data from a novel lens. Thank you for your time today, and I look forward to any questions that you guys have.
Thanks for that. It's an interesting talk. Are there any questions? It's a minute or two. So I guess I've got one question. What do you think the correspondence between information gain and something like human interest, or so you're splitting the plans up into sets, right? Do you think there's some other criteria that might be interesting, some bias on the way you construct LTLs?
Right, that's a really good question. So the actual quality of a given specification to a specific problem or to the preferences of a human, we would rely on the Bayes LTL framework for the human to incorporate their preferences into the discovery of the specifications. And then given the human's preferences, we would use metrics such as average depth to measure the quality of the specifications generated within the constraints that the human provides. So for an example, like a human might provide, a human might prefer a certain template over another.
Yeah, okay, thanks. I guess the other thing is, are you think, so at the moment you do sampling and then you make a random allocation teach to the positive and negative, right? Are you thinking of a more direct way of constructing LTL, or are you finding that this approach is coming up with is an effective way of coming up with LTL?
Certainly future work should focus on like intelligent ways to better inform future splits from previous splits, but relying on the randomness of dividing a parent set into two subsets and then using existing contrastive explanation frameworks to develop relative or relevant LTL. That's sort of the best that we have right now to work with, but certainly future work can open up a lot of different options to look at this.
Yeah, cool. Thanks. That's interesting work. Okay, moving on to the last talk in the session. It's Explainable Pathfinding for Inscrutable Planners with Inductive Logic Programming, and is Forrest sharing their screen? Yeah.
Okay, can you see my screen?
Yes, thanks.
Okay, thank you. And thank you for putting on this workshop. So in this talk, I'm going to go over the motivation of what we're doing, then describe the DeepCube algorithm, and then talk about how that fits into our explainable planning algorithm. I'll talk about some preliminary results where we apply this to towers of Hanoi and what type of explanations are produced. So with planning problems, we can see them in all different types of fields. So for example, in some previous work that we did, we looked at solving planning problems using artificial intelligence when we were focusing on puzzles such as the Rubik's Cube, but you can pose problems in mathematics such as theorem proving as planning problems, problems in chemistry, problems in program synthesis, and problems in robotics. And so one of the big motivations behind this work is not just finding solutions and explaining them to humans, but doing this in a collaborative way. So we want to be able to allow humans to share questions that they have and share ideas that they have. And this can be applied not just to problems in education, but also in knowledge discovery. So on the frontiers of research, imagine you have some unsolved problem, and perhaps you won't be able to solve it by yourself, and maybe AI won't be able to solve it by itself, but you can create this positive feedback loop where you're learning from AI and AI is learning from you. So that's the ultimate vision of this research, is to apply this to problems involving knowledge discovery. So the underlying algorithm and how we're actually able to solve these planning problems is what we call DeepCube. And so the algorithm is actually fairly simple to understand. We can do approximate value iteration. And so we are learning some cost to go. And when doing this approximate value iteration, we can try to just greedily behave greedily with respect to the cost function that we learn. So the cost function is represented by some deep neural network, and we can try to behave greedily with respect to that. Now, if you do this, you'll see that you're not going to be able to reliably solve the problem because there's going to be errors, approximation errors. And so you can then plug this approximate, this cost to go function into a search method, say A* search. And from this, you see that we're actually able to solve all of these problems in these puzzles here on the bottom left. And a lot of the times we're actually able to find the shortest path. So here are the results that we got when we were doing DeepCube and applying it to these puzzles. And so you see for the Rubik's Cube, we're able to find the shortest path 60% of the time. For the 15 puzzle, we're able to find the shortest path almost 100% of the time. For puzzles such as lights out, we were able to find the shortest path all the time. And we were able to do this on the order of seconds. And so while we're able to solve these problems, you don't learn anything from actually observing the solution. So you can see this, solve the Rubik's Cube, but you're not necessarily going to learn anything new from it. And then when we were actually investigating what this neural network was learning, we found that it often found symmetric solutions to symmetric states for the Rubik's Cube, and it often used conjugate triplets. So that means it did some move pattern A, B, A inverse. Do some move A, another move B, reverse that move A. But this required us already to know about symmetry and conjugate triplets. And so there's not really going to be anything new that we can learn from it, but we know that there is the potential to learn something from it. So also these are just some applications of the DeepCube algorithm just to show that this applies beyond puzzles, so quantum computing and cryptography. But what we want to do is we want to come up with a framework for explainable planning. And so first we represent a solution to a planning problem as a logic program. Why do we choose logic programming? The reason is because we can define the predicates that the logic program can use, and we hope that the combination, the composition of these predicates is actually going to be something that we can understand. So logic programming is appealing for this reason. We're often able to understand just by looking at the logic program what is what's going on. So we get explainability fairly easily with logic programming. Now, we represent the solution to any planning problem as a recursive logic program. And so I have an example here where we have a set of clauses, and in each clause, we're going to have some precondition, macro action, and then a recursive call. And we have the base case when we reach the goal. And so this is how we are representing the solution to any planning problem. And if we are able to design our predicates appropriately, then hopefully this logic program will already provide some explainability. In future slides, I'm going to talk about how we're going to actually represent this logic program as a graph to find different ways that we can actually explain a solution. So we can take this logic program and we can actually create this graph. And in this graph, the nodes are going to represent preconditions and the edges are going to represent macro actions. And we're going to use this graph to find different ways that we can do explainability. So here you see on the left, the logic program, and on the right, you see two different graphs. Now, if you were to translate these graphs to a logic program, meaning you have your precondition, macro action, then recursive call, you're actually going to get the same logic program. But you have two different graphs, and the structure of the graph is actually dependent on the dynamics of the environment. So for example, if I'm here, I have a state that matches this precondition 3, and I take macro action 1. Depending on the environment, I could transition to a set of states that is going to be in the set by precondition 1, or I could transition to the goal. So this is just going to depend on the environment at hand. So this is to show how this graph actually provides you more information than the logic program would. So the logic program is going to give you the overall solution, but the graph is going to show you what the dynamics of the environment, how the dynamics are actually transitioning from precondition to precondition. Okay, so given that we are describing our solution as a logic program and we're representing this logic program as a graph, how are we actually going to construct these logic programs or construct this graph? So as we're constructing the graph, we're constructing the logic program. So let's focus on constructing the graph. So first, we're going to start with some set of states in the state space. So we can sample these sets of states, and then we can solve these states. just finding paths from all of these states to the goal. And we can do this with any pathfinding any solver. So in this case, we're going to use DeepQA because we can learn without having to have any human knowledge in terms of how you're actually going to solve the problem. So we can learn how to solve the problem without any human knowledge, and so we're going to use DeepQA. And then we can look at all of these trajectories, and each of these trajectories is going to represent a macro action. And so we can extract all the different macro actions, and then we can see for some macro action, which states is it actually going to find a path to a goal node. And so any of the nodes that are already in the graph, we can think of as a goal node. So anytime we're able to connect some state to a node in the graph, we can say that this is finding a path to some goal node, because once we're able to connect it to the graph, we're able to solve that state. And so we're going to start out with a graph that only has the goal. And when we find paths to goal nodes, what we do is then we're going to use inductive logic programming to find that precondition. So we have the macro action and we want to find the precondition, and we do this with inductive logic programming. Now, the benefit of using this inductive logic programming is that only learnable preconditions are going to be added to the graph. So you may find a path to the graph, but you're not able to learn it. And this actually is a good thing, because this is going to prevent you from adding edges to the graph that you cannot explain. So if we're assuming that if we can learn that precondition, we're able to explain it, then only explainable nodes are going to be added to the graph. And we're going to repeat this process until all states match a precondition. So here's a visualization of this process. We start out with a graph that only has the goal node, and we find paths from the existing states to the goal, and we can then learn maybe one or more preconditions. And we have here this edge is the macro action, and then we can repeat this process. So say we're not able to learn a precondition for this one here on the right, perhaps we can then learn preconditions for states that have paths to the new goal node that we actually learned. So we're not always going to want to find paths directly to the goal. We can then build off of other preconditions that we've learned. And so this is actually similar to a dynamic programming approach. We want to find, we solve subproblems, and then we can then build on those subproblems to solve other problems. Okay, so the inductive logic programming framework that we use is Popper. And of course, we're able to define our background knowledge in something like Prolog, but Popper has a very convenient way to express inductive biases. And this was very helpful for our experiments because we can express somewhat complicated inductive biases that allow us to learn programs faster, but also allow us to learn programs that make more sense to us. So we looked at different ways of looking at this graph and then producing explanations. So the first way is actually not dependent on the graph. What we can do is we can look at the macro actions, and we can look at macro actions that are the same, and then we can try to learn a precondition that's going to summarize when you just do that one macro action. So say, for example, the macro action 1 is repeated 5 times and has 5 different preconditions. What we can try to do is we can try to learn a program that's going to be useful that's going to describe actually those 5 scenarios. So we can try to summarize those 5 scenarios into just one. And then we have this if-then structure. So if this, then do macro action 1. If that, then do macro action 2. Then when we actually come to use the graph, we can try to find hierarchies by summarizing ancestors of nodes or summarizing descendants of nodes. So we can look at a node and look at all its ancestors and then say, can we learn a program that differentiates the ancestors from the descendants? Or we can flip it, can we learn a program that differentiates the descendants from the ancestors? Okay, so the environment that we our preliminary work was done in the Towers of Hanoi environment. And so the background knowledge we had was fairly straightforward. What are the disks in Towers of Hanoi? What are the pegs? When is a disk on a peg? Which disks are smaller or larger than the other? And then for our inductive bias, we also had something fairly straightforward. So for example, disks and peg can only have one name. You can't have more than one disk or peg with the same name. And a disk can only be on one peg. So this can't be on, say 2 pegs at a time. All right. So when we are summarizing, after we've constructed the graph and we want to say summarize macro actions that are the same, we then get this following structure. So say, for example, if disk 2 is above disk 3 and disk 1 is not on peg 3, then you want to move disk 1 to peg 3. And I think there were 7 different macro actions. And so these all consisted of moving some disk to some peg. But keep in mind that we weren't able to learn this for all the macro actions. We were able to learn this for 5 of the 7. And so this shows that there is some limitation here, but there are different ways that we could actually explain the macro actions. And maybe a more expressive background knowledge or a more flexible inductive bias is going to allow us to learn this, but this may come at a cost of the program being not as explainable. Then another thing we can do is we can summarize the ancestors. So start from a node and summarize its ancestors. And when we do this, we get the following graph, which is actually identifying the hierarchical structure of the Towers of Hanoi problem. So this one you can think of as a hierarchical node here is saying disk 3 is on peg 3, and then you come from these 2 different scenarios where disk 3 is on peg 2 or disk 3 is on peg 1. And so this is that hierarchical structure that you actually are observing in Towers of Hanoi, and we were able to discover it by summarizing the graph this way. And then from summarizing the descendants, we get a smaller graph. It's still not as explainable. So this is the structure that we get. It still requires a good amount of reading. It's not immediately clear what's going on, but you do get a smaller graph. So it's smaller than before, and perhaps in scenarios where you have very complicated problems, these methods of finding hierarchy can drastically reduce the size of the graph. So that's what we're hoping to show in future work. And I just wanted to acknowledge my students, Regina and Vedant, who've been working hard on this project. And here are just some references. And are there any questions?
Thanks for the talk. So that the time's over, but so we're going to have a 15-minute break until 10 past. I'm happy to wait while we have a question if anyone's got one. Michael, do you want to go for it? But we are having a break, so if you want a break, then go now. So 10 past. Okay, thanks.
Okay. Thank you for the talk. So I'm a little bit confused here. What is your actual setting? So what do you assume to have?
Sure. So when you say what do we assume to have, do you mean
like do you have like a logical representation of states? Do you have a set of actions that are represented by labels only? Do you have action models? What are your assumptions?
Oh, okay. Yeah, so we assume that we have a model of the environment. We assume that we have logical representation of states. We assume that we have the predicates that say, what is a disk, what is a peg. We assume we have this inductive bias, but we don't assume that we have any logical representation of solutions. And so this is what's being learned. So we have the predicates, transition model, solver.
Right. But you could apply any planner, right?
Yeah.
Okay.
Yes,
So And the text that you have shown at the end of these macros, is that something that the user supplies? Like if
that's a good question. I didn't explain that properly. So with these yes, so with this text, what we have is a simple what's called template-based model for generating natural language from these logic programs. Thanks for that. I actually didn't explain this at all.
So that's an output. That's an output. That's not an input.
Exactly. So we have the logic program, and then we have this template-based model for just generating this text.
Right. But this output is, I mean, in planning, what we call macros is a little bit different, right? So you usually have macros or sequences of predefined sequences of actions, right? It could be, right? It could be something a little bit more generic, but these are actually something like tasks in HTN, right?
No, because this wouldn't be task. This is simply an if-then structure, and if you just repeat this this process, you would just repeat this until you find a solution. So you just
right, but I'm looking at the first, right? So it doesn't say anything about the location of the disk, right? Disk one, right? So it could be the case that you actually need to dig deeper, like free stuff from disk one in order to be able to move it to peg3, right?
That would no, because since disk 2 is above disk 3, then disk 1, this is a 3-disk tower of noise.
Oh,
so,
I see.
Yeah.
Okay,
yeah,
I see. Okay, then this is just a precondition of an action, right?
Exactly, just like
extended precondition, yes. Right? Right. Okay, I see. Thank you.
Thank you.
Great, cool. I think if we can move anything else onto Slack and we'll just actually have a break for a bit, that would be good. And I'll come back at 10 past. Okay. Thanks. Great talks.
Unfortunately, the speaker for the first paper couldn't make it, so we have to skip it. But we will try to request a video of the talk so we can add it to our webpage, so you can check it out later. So then the second talk for this session is by Sarat, so the stage is yours.
Thank you so much. Let me share my slides. Can you guys see the slides?
Yeah.
Okay.
Yeah.
Okay. Hello, everyone. My name is Sharad, and I'll be talking about our work. Why did you do that? Generalizing causal link explanation for a fully observable non-deterministic plan problem. So this is joint work with Christian Hughes and Rao. So I'll just get started with it. So hopefully, like people who are like familiar with like XAIP work would generally know of causal link explanation. They're quite popular, and in some sense, you could understand them as trying to answer the question, why is a particular step required in a given plan? So if you think about a plan as a sequence of actions, you have the sequence, and then some step, let's say step A, like there's a step for an action A, and you're asking the question, why is AI needed for this plan? Generally, the explanation here would take the form of a causal chain, where you would have basically the chain consists of facts, like basically causal links that are contributed by that action, which no other contributed. The chain is
the chain goes all the way towards the goal. This kind of explanation has a long history within planning and XAIP itself, and they correspond to this concept called well-justified actions, which is pretty well established, and it's kind of been there for a while. And basically, in some sense, you could understand them as kind of establishing the fact that if you were to remove this action is required, because if you were to remove it from the plan, right, the plan would no longer be valid. So this is part of, there are other notions of justified actions, and there's a larger class of it, and you use like a very special case. So this was the background for causal link explanation. In this particular work, I want to motivate looking at this explanation from a more general standpoint. So we want to go beyond just classical planning problem, and part of that requires you to go beyond sequential plans, right? So that means looking at other forms of solution concepts like policies, controllers, and so on. And as we will see, this generalization requires us to take a more general view of what it means to have how do we kind of ground the concept of a causal link in these general settings? How do we talk about solution minimality, and how do we talk about well-justified actions in this more general setting? So that would be that's the goal of this particular paper. Specifically, we will be going to be looking at this class of problem called formed, a fully observable non-deterministic problem, where actions could have qualitative non-deterministic effects. That is, unlike in classical planning, where we know what exactly would happen when an action is executed in a state, here there's a set of possibilities, and one of those possible outcomes could happen. So there are different notions of solution concept that has been investigated in this context. But in this particular paper, we focused on this idea of looking at policies as a solution to problems. So there have been different notions of kinds of problem solutions, like there are strong solutions, strong cyclic solutions, weak solutions, and so on. I won't delve too much into those, but rather the part that I would want to focus on is the fact that we have a formed problem where there are fully observed state actions with non-deterministic effects, and the system, the planner, is giving us a policy as a solution to that particular planning problem. So here's an example setting. Okay, we have this problem of you're trying to go from your home. The planner is trying to come up with a policy that will tell you what to do. How do you get from your home to, say, your office? Okay. And there are various actions within this policy. So it could be things like, okay, you have to drive from some place to somewhere, and you have even actions like, oh, you have to order donuts, and there are things like there are non-deterministic effects, like, okay, if you order donuts, you might not get the kind of donut you want. There might be other options, and so on. So there are non-deterministic effects, and you're basically given this policy, right? So there are these contingencies, and there are these branches happening. And you want to go back and ask the same question we did in the classical plan setting, which is, do I really need this action, right? So the question was, the question was, we asked the same as we had in the classical plan setting. Let's say in this case, you are at a state, you are at home, that's your initial state, and the policy says you have to do an action called order donuts. Okay. That's just the action that the planner recommended. And you would like, as an explanation, ask, why is this action required, right? So we can now revisit one of the concept we had before, right? The idea was, okay, if we remove this particular step from the policy, can we still think of this policy as being valid in some sense, right? And this is where we run into our first problem. Right? What does it actually mean to remove a state action pair from policy? Because after all, if you are thinking about executing a policy, you only know what to do at specific steps, right? At specific states. So if you don't execute the action order donut at home, there's no meaningful way of thinking about, oh, how do I execute the rest of the policy? So we run into our first issue here.
So does that mean that every state action pair in a policy is required, right? Our policies by default like only consisting of required state action pairs. If that was the case, we could have gone back to our classical planning problems, right? Taken a plan and shown it or presented it in the form of a policy, and we would have gotten over the problem of whether there are required actions, right? There's well-justified action. So the answer is obviously no, right? There could still be well-formed policies where there are actions that can in some sense be kept, or that is not really contributing to the overall objective of getting to the goal, right? And this requires us to kind of revisit the notion of what does it mean to have a well-justified action. So we go back to our policy, and now we'll take a different view of what these policies consist of, right? So instead of thinking about them as policies itself, we can think about them as a set of traces, right? From a given state, these traces would all could possibly take you to a goal. Since there are loops and things like that, this could be a countably infinite set of traces, but they are traces nevertheless. And I'll put forth a new definition of well-justified action here, which is basically that a state action pair is well-justified for a policy if for every individual trace we could have sampled from the policy, there is a corresponding step that is well-justified. So in some sense, if I had removed that policy state action in some sense, so like there was a way I could remove that, there is at least one trace that could have taken you to the goal that no longer works. So this would be the notion of well-justified policy that we will kind of follow through in this one. Okay, so first of all, just to establish that this is a well-formed notion, if you just think about it, mapping it back into a classical planning problem, you can see that this is a genuine generalization of what we have. Because what we see is when you go back to classical planning problem, the set of traces turns into just a singleton set, and the definition still holds. But now the question is, okay, I talked about how the number of traces could be like countably infinite, right? So how do we even like test whether an action is required, right? Well justified. So the specific technique I'll actually use is something which is basically leverages a compilation to a classical planning problem. So we'll take the non-deterministic problem, do something called as an all-outcome determinization, which is basically we'll take a non-deterministic action and assume that we could have deterministic versions of that action that would create any of the outcomes we want as required. So this is a very common technique that's used in solving these kind of fun problems. So we'll have an all-outcome determinized version of the problem. And what we will do is we'll have a compiled version which will keep track of two copies of the fluent. One copy of the fluent is basically to kind of one set of fluents would correspond to basically the execution of the policy. So we'll have one copy of fluents which will just try to maintain this progression in the policy, and the other set of fluents will only be used by precondition. So this the point about an action being justified is in some sense connected to whether it contributes to the preconditions of the user action. So we'll have a set of copy there. And then what we'll do is in the compilation itself, we'll have one action for each state action pair in the policy. So what we'll do is we create a new planning problem. There is a action for each state action pair, and the preconditions for that action look something like this. So you would have like one part of the precondition that corresponds to the policy itself, which is defined in that particular fluent set, and then you'll have the original preconditions of the action. I know this kind of looks a bit complex. So what I'll do is let me just switch it to the specific example we were using, which is basically this. So let's say we had the policy had said there was a drive action, okay, and the drive action has to be done at a state where there is a set of donuts have been ordered. You were at a particular street, and the street where you're going to were free. This was a state where that action was to be executed. So you have a set of precondition that corresponds to that state, which is defined under the subset of fluent prefixed by this symbol phi. Okay, so that you have that. And then you had the original preconditions of the action on drive, which only required that the street is free and you are at a particular street. And as the effects of the action, you have like two versions of that effects. One version that updates the fluents which are defined for the policy, and one set of fluents that would one set of effects that would update the other fluents. So in some sense, each execution of this action will allow you to like progress through the policy and also make the changes in the other fluents at that. And what we do for testing whether a particular action is required is we will go back to this definition, right? We'll keep the precondition as it is, but in the effects, we will only keep the effects that was meant for the policy fluents and not the other ones. So what this means is basically this action that we are testing can now allow you to execute the rest of the policy, but will not contribute to the precondition. So in some, it is letting you execute policy without right. If it was not well justified, right, then you could still have plans because it will let you execute it. And so that is the basic idea of testing, which is basically you have these kind of compiled planning problems, and you're looking for the solvability of that problem. So if it is unsolvable, that means there exists no trace that could have taken you to the goal which doesn't use this action. So this way we'll know whether or not an action is justified. Okay, so this was all to describe when an action is required. But then there's the question of how do we explain this, right? That was the bigger question, right? So that's where I started, right? So we want a way to explain, provide something that's similar to causal link explanation in this setting. So the problem was, as we said, there are these individual traces that correspond to this one policy, and you could have in theory come up with causal link explanation for each of these traces, but there's a large number and you can't really effectively show it to people in a meaningful way. So what we instead do is, in some sense, summarize this entire set, right? Rather than talking about individual traces, individual causal links, we will talk about sub goals which the policy has to achieve. So in this case, we take a chain of sub goals such that the first sub goal in the chain was something that was required that can only be achieved if the current state action pair in question has been executed. Yeah, so I think I'm kind of running out of time. So, but I think just as a quick example, this is how the sub goal chain would look in this particular case. So the question of why was the order donut was the action was required was to get to the sub goal that the security guard has to be bribed and so on. So this is basically how the explanation would look like, and I won't go into too much detail because we don't have the time. But this sub goal chain could have been extracted from the landmarks of the compilation I talked about earlier. So you can extract landmarks from that compilation to get to the sub goals. Okay, so we did some evaluation on the empirical properties, but the bigger thing I just wanted to end this talk with was just to kind of, this was a particular example where we took an explanation technique that existed from classical planning and just kind of demonstrated it in this more general case. And in this specific case, we looked at a causal link explanation and looked at how do we translate them into this more general setting. But we also see this as being a more general research agenda. One way we should look at techniques from which has been particularly designed and developed for classical planning settings and see how they might translate into this model. So that's it. I'll end my talk with that, and be happy to take any questions.
thanks. So we have a question from Ben.
Yes.
Thank you for the talk. Great talk. So maybe because of the compilation approach that you use to track the causal links, you had to go over it a little bit quick. So maybe I have to go into more detail with it. But it seems maybe I'm wrong, and just tell me I'm wrong if that's the case. But it seems that this is just for what Fink and Yang call justified actions rather than perfectly justified. So it could be that you just remove a set of actions and it's still required for the plan. So, I mean, have you thought, because we used a similar approach for something that we needed to do, and we, you know, it was a much more difficult problem to come up with this perfectly justified. I'm not sure if you thought about it or what you think about that.
So first of all, you're completely right. We only looked at well-justified action, not strongly justified action. The reason for that was because the current explanation system only looked for that kind of validity. It was not looking for perfectly justified actions. And honestly, I haven't thought about like the subset removal kind of a problem, but that is definitely something that we would like to look at as we go forward.
Yeah. I think potentially it might be having to search over some sort of changes of these, but if you come up with a more elegant solution, you know, let me know.
But it's also there are two problems here, right? Like translating the notion of justified and well-justified actions sets, well-justified policies into plans into the context of font, and there is also the question of like when they would correspond to explanations, right? So so the question is like, what would be the explanatory query that correspond to something like strongly justified subset? Are people going to ask, is this subset strongly justified? As in like, do I need this subset of action? Then the compilation is much easier, right? Because then all you need to do is you're going to take out the subset and see if things still work. Right. So So there is two aspects to it, and depending on the aspect, things will be.
Great. Thank you.
David had.
David.
Yeah. So you started to get at this, or at least hint at it in your conclusion slide, but this is a very black and white notion of whether or not something is causally required. And you can think of an action as you know, what you'd like to see is, well, this is required most of the time, or this is required only some of the time. And even when you don't have a probabilistic.
No, I completely agree with it. Yes, and that's something we also mentioned in the paper. There could be other notions of what it means to have a justified action in this kind of context. We just went with the simplest one as a starting point for this, which was it doesn't work.
I mean, so generally in the old days, I think God knows how long back, people basically would extend the causal link based approaches for everything. And so you almost construct, as Dave is saying, you construct by shoring up support, by adding additional causal links and so on. And so you can actually provide it as an explanation. Even when like Chang came up with his paper, it basically had no mention of causal links. He was just saying, if the plan has been thrown to you, how do you explain it? You know, I think, but in general, using causal links to explain that this kind of adds to the support is a way to extend it to, I think, you know, probabilistic plans too. But I still, I mean, as you know, I mean, I think I'm not completely sure whether causal link based explanations, and those are like the first things people have tried. I think it still is really a question of what do people think about the problem, you know, and so with respect to the MRH model. But this is sort of being tried for even more things like, you know, probabilistic plans.
To me, this also comes under the question of summarizing things. So, like, you're trying to understand the policy itself.
Okay, thanks for the discussion. And let's move on to the next or last paper of the session. Yeah. Stylianos, it's your turn.
Yes, one sec. Let me share my slides. I don't see. Okay. Now, can you see the main or can you see the presenter?
The presenter.
Okay,
So we
let me,
see.
yeah, let me fix that one second. Let's see. Okay, I think it's a display.
We actually like the presenter.
So for some reason,
Often if you disconnect an external monitor, it helps.
yeah, I did. So
there's also an option on PowerPoint that you can do to switch the screens from presenter. I can't remember where it is.
Let me see. Yeah. Oops.
Yeah, that's fine.
Yeah, maybe just remove the Zoom window that's in front of the slides.
Yeah. Okay, now?
Yeah.
Is it still the presenter or the main?
That's the main.
Okay, all right, all right.
Slides.
All right, thank you, Rebecca. Hello, everyone. I'm Stylianos, and I'll be presenting a short paper. This is a joint work with William Yo, my advisor. And in this paper, we're basically interested in coming up with more or less general method for generating abstract explanations. And this method is knowledge forgetting, as you can see in the title. But first, so the main idea in this paper, I guess it's predicated on the model reconciliation, which most of you are familiar with, I suppose, which is, has been formulated by Chakraborty in et al. And others in Professor Kamabani's lab at ASU. But in this paper, we consider the logic-based formulation, which we formulated with William and Causal. So let's quickly unpack this definition. So assume we have two knowledge bases of an agent and the human user. Basically, let's say that the knowledge base of the agent encodes the agent's model of a planning task, and KB8 encodes the human's model of a planning task. And now the knowledge base of the agent entails a query, let's say the agent's plan, and the knowledge base of the human does not entail that query, right? So the goal of the logic-based model reconciliation is to find an explanation, that is what to add from the knowledge base of the agent to the knowledge base of the human, and what to remove from the knowledge base of the human in case there are inconsistencies, such that if we use this information to update the human's model, the knowledge base of the human, then the knowledge base of the human will entail that query, right? So this is a very simple definition of the logic-based model reconciliation. But now, however, this comes, the definition of model reconciliation comes with some assumptions, and some of these assumptions are that the human's model is known to the agent a priori. So the agent has in possession of the human's model, and it's at the same abstraction level as the agent's model, right? And now this, although may lead to explanations that are not very intelligible by the human user. So in this work, what we're interested in is relaxing this assumption and assuming now that we have a human vocabulary. instead of a human model that the agent has. And this human vocabulary basically is the terms or letters of let's say, a specific task, let's say a planning task, that the human knows. For example, if it's a planning task, then it will be, the action names, the precondition names, all those stuff. And the high-level idea is to use this human vocabulary to generate explanations at an appropriate abstraction level. And we're going to see now how to do that. And we're going to do that, yeah, with the knowledge forgetting, which is a logic-based operator. And at a high level, knowledge forgetting reduces the agent's language by forgetting letters, let's say terms, from its vocabulary, right? And interestingly, this knowledge forgetting has been formulated by originates from the mid-1800s by George Boole, which wrote about this in his paper on the investigations of the laws of thought. And just for the sake of of this presentation, for the sake of time, I will try to give you the most basic definition of knowledge forgetting, which is based on propositional logic. So bear with me for a moment. So assume we have a propositional language expressed over a finite set of letters, a vocabulary, basically the atoms of the language. Now, to forget a letter from the vocabulary is simply done by performing all possible resolutions with respect to that letter, and then add these resolvents to the formula that do not mention that letter. And this definition here is basically due to Delgrand, which is more or less a general definition of knowledge forgetting and can be applied to different kinds of logics like persuasive logic, modal logic, ASP, stuff like that. But for propositional logic is equivalent to Boole's definition from the 1800s. Right. So basically, we perform our resolutions with that letter, and then we add these resolvents to the letters that do not mention that, to the formulas that do not mention that letter. Now, to make things a bit simpler, let me give you a very quick example. So assume we have a single vocabulary consisting of the terms Socrates, Greek, human, and mortal. And yeah, this is a very contrived example. And we have the knowledge base that if Socrates, then Greek, if Greek, human, and if human, mortal. Like very simple rules. And we can see, of course, that this knowledge base, it is to see that it entails if Socrates, then mortal, right? Now, if we want to forget, let's say the term Greek, then how are we going to do that? Then the knowledge base will become. Excuse me. First, the formulas that do not mention that letter, the term Greek is, of course, if human, mortal, and the rest will be the resolvents, right? So if we resolve the first two formulas, if Socrates Greek with if Greek then human, and then it becomes if Socrates then human, right? So these are the resolvents, and this basically is the knowledge base if we forget the term Greek, right? So basically, you can see it's a simplification of the original knowledge base. Similarly, if you want to forget the term human, then the knowledge base becomes if Socrates Greek, and if Greek then mortal, right? And what is interesting here is that, as you can see, that these two modified knowledge bases also entail that if Socrates then mortal, right? And this is an important property which we will use in our formulation for exponential generation. We will see in the next at a later slide. So in general, you can think of forgetting a letter from a knowledge basis from a knowledge base as the logical consequences of the knowledge base expressible over the set of letters that do not mention that letter, right? So that's basically the knowledge forgetting operator. And in addition, what is very interesting to note here is that through knowledge forgetting, we can define an abstraction lattice, right? Where at the very bottom of the lattice, we have the original knowledge base that we have, the full knowledge base. Basically, we don't forget anything. And then at the first level of the lattice, we forget each of the letters of the terms. For example, here G is we forget the letter G, and then the knowledge base becomes if Socrates human, then if human mortal. Then if we go one level up, then we forget two terms, two letters, and then our knowledge base will become if Socrates then mortal, and so on. So basically, it boils down to finding the appropriate abstraction level, right? So what set of letters to forget from a knowledge base. Now, to formalize this in a more for an exponential generation setting. Now, assume we have the knowledge base of the agent and a query that is entailed by the knowledge base of the agent. Let's say a plan or whatever we want it to be, and human vocabulary. That is the subset of the agent's vocabulary. So we make also this assumption here. So the goal in this paper is to find the set of letters from sigma, and sigma is basically a minimal support that entails phi, such that if we forget this set of letters from that support, then it will entail phi. So the first question here is how to find the minimal support, which I'm not going to talk about in this short presentation here, but we have a paper that is on finding a minimal support from one knowledge base or two knowledge bases. And additionally, so the most, I guess, the most important question here is how to find this set of letters. So what set of letters to remove? So one way is the naive, of course, way is to basically forget all the terms letters that the human doesn't know, right? And keep only the terms letters that the human knows in your explanation, in your support. So that's also, as you can think, very naive. Or we can define some sort of vocabulary importance, right? And then forget the least important, let's say, letters from the explanation support. And this can be done either by defining, let's say, a weighted vocabulary where each term letter has a specific weight signifying the importance. Or a more mathematical, let's say, formulation where we can simply say that importance is the number of formulae that mention that letter divided by the number of letters of those formulae. Basically, the frequency in the formulas of the letters that we want to forget. Yeah, so, okay, because I think I'm running out of a bit of time because this is a short presentation. So yeah, so this is the main idea of the paper is to have a more or less a general method for generating abstract explanations for human users, let's say, given a human vocabulary. So, and if I can squeeze in something very briefly, is that, excuse me, so we also conceptualize that these abstract explanations can initiate sort of a dialogue between an agent and a human user. So imagine we have an agent, which now the agent's model consists of its own knowledge base and also an approximate knowledge base of a human user, right? And then through we'll also have communication medium, so they can communicate with each other. I'm not going to talk about this right now. And then imagine that the agent generates, let's say, an abstract or an initial explanation, which gives to the human through the communication medium. And now the human will have the ability to respond to the agent's explanation, let's say, and either, let's say, request to increase or decrease the granularity of the explanation. So basically want to traverse, if you remember, the abstraction lattice up or down to find the appropriate abstraction level according to the human's request, or refute this explanation, let's say through argumentation of some sort. And then the human will pass this along to the agent. And then what I want to convey here is that through this process, then the agent will be able to take this information from a human and use it to update the approximation of the human's model that it has to a more accurate, let's say, model. And I think I'm out of time. And yeah, this is all.
Thanks a lot. Are there any questions? Yeah, Sarat?
So great work. Just had a few clarification questions.
Yeah.
So I've personally worked on some versions or variations on model reconciliation which uses projection-based explanation. So it is in some sense very similar to like the way you're talking about vocabulary forgetting, because what projection-based explanation generally does is you're removing the fluent from the model basically, and it takes a very similar form. And that work also had through like abstraction methods and things like that. So I was just wondering, are you aware of that work, and like how would you separate what you're doing here from that?
So,
obviously, there is the point of you're looking at like knowledge bases as opposed to like specific.
Right. So yeah, I think I know what paper you're talking about. I think it's about the state abstractions, right? Where a human gives a FOIL. Is that the work you're talking about?
Yes, that's the particular one. But the state abstraction itself is formed by like fluent projection. So you take a subset of proportional factors, and then you're projecting it out. So your projection, usually in strip setting, projection is usually just removed and
right. So I guess in that sense, they're quite similar. I guess at least for planning tasks, right? I think. However, with this method, we wanted to have a more or less, as I said at first, general method. So if you have, so you're able to do this for any knowledge base that encodes any kind of problem. So even beyond planning. So I guess that's the main distinction. But I guess for planning is more or less similar to your paper, to the state abstractions, where you project where you project out the predicates, and stuff like that.
Yeah. So I think like there's also so one of the things I just probably want to add is usually projections is one type of transformation you can do. There are other things also you can consider, like you can look at like decomposing the problem. Like usually in planning, so like there are like a specific transformation that makes a lot more sense in the planning context. Maybe so one interesting thing might be to see how those kind of like model simplification things would map over to these models.
Right. I will need to investigate that further to answer accurately. But yeah, thank you. That's a good point. Thank you. Yeah.
Okay, thanks. Michael, you asked a question in the chat during the talk. I'm not sure whether it's whether you want.
That's basically the same question that Sarat asked.
Okay. Okay, then that's it for the third session, and we now have a short break until the full hour, depending on where you are. For me, it's 7 o'clock, and then after that, we have the first invited talk for our workshop by Mark Riedl. So see you in about 10 minutes.
So hello, everyone. I'm quite excited to invite everyone to the first invited talk for XAIP-22. So the talk is from Professor Mark Riedl. So I'll just give a brief intro, and then I'll let Professor Mark take it from there. So Dr. Mark Riedl is a professor at Georgia Tech School of Interactive Computing and is the associate director of Georgia Tech Machine Learning Center. So Dr. Riedl's research has been focused on human-centered AI, which is the development of AI and machine learning techniques that understand and interact with humans in more natural ways. So Dr. Riedl's recent work has focused on problems like story understanding generation, computational creativity, explainable AI, teaching virtual agents to behave safely, etc. And his research has been supported by NSF, DARPA, ONR, the US Army, US Health and Human Services, Disney, and Google. And he's also the recipient of DARPA Young Faculty Award and the NSF Career Award. So please, Dr. Riedl, go ahead.
All right, thank you very much, Sarat. That was a very kind introduction. I assume everyone is seeing my screen and everyone can hear me. I can't hear or see you, so just shout if something has gone wrong. And I'm very, very delighted to have been invited to come and join your remarkable little community here. I guess a longtime reader, first time caller. So, you know, I was invited to talk, and I really thought really hard about what it was that I wanted to speak about here. And I realized that what I really wanted to do was tell a little bit of the story about how I accidentally became an explainable AI researcher in this kind of new and emerging field called human-centered explainable AI, or basically explainable AI crossed with human-computer interaction. And I promise my talk is not about Twitter, even though I have a screenshot of Twitter. But I put this up here just to kind of convey the notion that we are progressively and increasingly surrounded by AI systems out in the real world. AI is no longer in the laboratory. It's in our pockets, it's in our cars, and it's in the algorithms that mediate our social media. And as this happens more and more, every time we find ourselves shouting at this computer because it does something stupid like an autocorrect, we are in some sense crossing into the realm where we need to think about explainable AI in commercial systems. So explainable AI for commercial end users. And I said this is going to be a little bit of a story about how I ended up coming to work on these sorts of things. And I will kind of start talking a little bit about where I was many years ago. When I first left school and got my first job, it was at a place called the University of Southern California Institute for Creative Technologies. If you've never heard about it, it's not really important. It's a soft money think tank that was funded by a combination of the US Army and Paramount Pictures. And yes, it's that weird. Our office space was designed by the set designer for Star Trek: The Next Generation, which makes for a fun space to work in, but it's not really that practical. But that's not really kind of part of the story. Why I was there is because the US military was really interested in bringing virtual characters, virtual agents into simulation environments to teach commanders and leaders to lead virtual platoons. And the issue that, and I should say this, in 2006, that was before we invented color photography. So we all saw in black and white. No, it was a time when conference papers still required us to put things in black and white, sometimes to publish. But anyways, what they were particularly interested in was something called after action reviews, which was what they would do after a particular mission was performed, whether in real life or in virtual. And they would want to kind of go back over things and understand why virtual characters did the things they did. Did they do the right things? Did they do the wrong things in the wrong time? And why did they do those things? So my job at the time was to generate behavior plans for these virtual agents that were explainable. And as we've seen throughout the day, you know, one of the ways we do this is we fall back on causal link planning. These are the sorts of things I did. Now, I never worked on the explanation systems. I worked on the planners, which eventually got me into this idea that these little missions were stories and I should do story generation, and spent a lot of time from that point forward doing stories, story generation, interactive stories, and so on and so forth. And this was all ancient history because I was at Georgia Tech, and it was 10 years later. And in sometime around 2016, I started seeing this explainable AI come back again. But this time it was different. It was about neural nets. It was particularly about vision systems, about Deep Dream trying to understand why these vision systems were generating the images they were, or what the vision systems had seen. And from that point, we branched out to natural language and reinforcement learning and all sorts of other things. But at the time, I was thinking, holy cow, I understand explainable AI, but from a different kind of perspective and a different kind of period in my life. Is there something that I should do from a research angle to bring my expertise into this kind of reinvigorated field of explainable AI? And I saw, and as I thought about it, I thought there was kind of two big things that were missing. So first of all, most of the work on explainable AI was really focused on helping developers and neural network developers in particular debug and improve their models, which is important. We want good models, of course. But I started thinking about all the different ways in which AI systems were integrating into our lives, even in 2016. And we can see a whole bunch of examples here on the screen. Which meant that increasingly AI people without technical backgrounds or computer science backgrounds or have any understanding of artificial intelligence were going to be interacting with these systems. These systems were going to do strange things. They're going to make mistakes, and it's going to leave people scratching their heads. And I also thought about, well, if we were to explain things to consumers, to end users, non-technical end users, what sort of modalities would we want? And natural language seemed like an interesting way of proceeding because it's the most accessible form of communication with any sort of system, right? We already know how to speak, we know how to understand language, whereas we might not understand visualizations and graphs and things like that. So that was kind of the first thing that I started thinking about. Why was no one working on, or why weren't many people working on consumer-facing AI systems explainability? And the other was, I was thinking a lot about reinforcement learning. So I think we all kind of know that sequential decision-making agents are especially hard to explain. And that's because, you know, decision is a function of some sort of goal or some sort of future expected reward. And particularly in terms of reinforcement learning, if we were to think that these are going to be particularly useful in consumer applications of the future, they operate on these policies. And these policies, they throw away a lot of information about why actions are done, right? So if we look at this simple grid world here, and we have an agent that goes on the particular path across the top of the screen, right? It might be very natural for us to kind of ask the question, well, why didn't it go down? Why didn't it go the short way to the goal? Okay. It might be because we don't understand the significance of the danger of falling down stairs, but there's some sort of disconnect between what the user is thinking about and what the agent is doing to solve the problem. But the agent has also forgotten why the Q values around the stairs are low. It just knows that the Q values around the stairs are low, right? So add all that complexity, but then also say, hey, can we actually explain a policy in natural language? And these seem like really interesting, hard, challenging problems. Bringing in kind of my expertise in stories and storytelling, you know, we also know that experts often use storytelling to do explanations, right? Every time they answer a question like, how did I do something and why didn't I do something else? In some sense, this is a little story. So what I really wanted to know at the time was, can we tackle both of these problems, explanations for end users and explanations for reinforcement learning, by generating tiny little stories about what the agent was trying to do, what it did, and why it didn't do other things. Now, I'm going to, by and large, fail at most of these goals, but that is the nature of research. And so kind of for this talk, I thought it'd be kind of useful to kind of talk about two things. One is how I started out thinking about algorithms, designing algorithms for doing explanation, and ended up studying humans, and then how I was able to take some of the things that I learned about studying humans and then come back to the algorithms to come up with new algorithms for explanation. And so we'll just kind of start with how we ended up studying humans. And again, this is in 2016, 2017, something like that. And I was thinking about these stories, and I was thinking about what we could do. And we really kind of, my team and I really kind of spent a long time thinking about how do humans, what happens when humans explain to humans, right? Maybe that's a really kind of good place to start. And well, you know, if you think about this way too much, right, which we did, we kind of come across a few observations. So first of all, humans don't know how the brain works. So they're not explaining how the brain. So an explanation is never how the brain works. It's never, oh, I was late for dinner because some of the neurons on the left side of my brain were firing when they should have been firing on the right side, right? I mean, that's not an explanation that would ever get you out of the doghouse, right? Trust me, I know. But what humans do is they invent a set of reasons, possibly reverse engineered to appear to be logically justified, but often the behavior is not logically justified. But they're looking for a set of reasons that are going to justify those behaviors to someone else. And they don't have a lot to do with the actual mechanism that created the behavior to begin with. So these are called rationales. We make rationales all the time, and we pass them off as explanations or justifications, right? So we thought, well, maybe what we need to do is these little stories that we're going to generate about agent behavior in reinforcement learning systems or whatever are going to be rationales. We're going to do rationale generation. We're going to generate a set of reasons or a logical basis for a course of action. And what good are these rationales going to be? Because they're not exactly describing the mechanism. Well, we came up with this hypothesis that people are going to feel more comfortable with technology that does generate rationale, which is comparable to the explanations that humans would produce. So in other words, these agents will start to feel like humans in terms of their rationale or their explainability. And that's going to put people into a frame of mind that they could possibly maybe trust the agents. Now, a few things to note, because there's probably a few things that are going through your mind. These are often things that come up, right? Rationale generation, we're not proposing to open the black box. Matter of fact, we're not looking to inside the black box at all. So this is kind of a very different way of thinking about explainable AI. Rationale generation does not guarantee what's now being called faithfulness, which is that it accurately conveys the mechanisms inside the decision-making agent. What we'd hope is that it correlates very strongly with how the agent actually makes decisions, but there's no kind of strong guarantee that we can make. And ultimately, what this is all about is if it's not about faithfulness, it's not about what's actually going on inside the black box. It has to be about what's called actionability. And actionability to me is one of the most important concepts in explainable AI, because what we want to do by creating explanations is give users the ability to make actions. And if your actions are not, I'm going to change the model, or I'm going to debug the model, or I'm going to collect more data or retrain my agent, right? Which is what developers do when they think about explainability. What are the actions that an end user, a non-technical end user, can possibly do, right? Well, they can do things like decide not to use the agent anymore, or not to trust the agent, or to change the operating environment to get the behavior that it wants out of the agent. So there are other forms of actionability. And in this case, our goal was to increase the acceptance of the agent's behaviors. We also need to do this in a domain, and I wasn't about to do commercial robotics, so we did Frogger, and we've already seen Frogger earlier today, so I guess that was a good choice. We all kind of know what Frogger is the goal to get past cars and over the water to the other side of the screen, right? And I'm going to just kind of assume we're all fairly familiar with the reinforcement training loop, right? Where the agent gets an observation and a reward from the environment, chooses an action from its policy that performs that, and so on and so forth. Now, because we're not opening up the black box, our rationale generator kind of wraps the agent, right? It takes the observations going into the agent, and it takes the actions going out of the agent. These are the two things we might be able to look at without looking inside the agent. And these become the inputs to some sort of rationale generator, which we'll try to figure out how to do, which ultimately is going to produce text to send to the human. And here's just kind of down in the corner, an example of, an explanation we might hope to see from a Frogger. So what's Frogger basically going to do here? Its explanations is basically going to be talking out loud. It's going to be, hopefully it's going to explain, it's going to talk about every single thing it's doing and why it's doing it at every particular moment as Frogger plays the game. Okay, so now how do we build this rationale generator? Well, we turned to something that was kind of hot at the time, again, 2016, 2017, which was neural machine translation. So neural machine translation was to use a neural network to transform a sequence of one language into a corresponding sequence of another language. And so our idea here was, let's just take the observations that the agent receives in whatever data structure it comes in, and the action, and call this a language, right? It's the language of Frogger. It's the language of our agent, or it's the language of the environment at least. And then we need to translate that somehow into a reasonable thing to say, which is the explanation. Okay, so now to do that, we're going to need both what the agent sees and does, which is easy to get, but we also need language, right, to translate it into. And so we had to do a data collection task. So we got 60 participants to play Frogger, but they didn't play just any sort of Frogger. We actually had them play a horrible version of Frogger that we created, where every time they took a move, they had 10 seconds to speak out loud what they were doing and why, right? And we would use speech to text translation to capture that information and record it. And then they would have this opportunity to go back and fix their text if there was text to speech transcription problems. That's kind of not important. The important thing here is, though, that we went out and we got human explanations, and we're actually teaching Frogger to emulate how humans give explanations. And we did that by getting humans to actually give us a data set of explanations. So in some sense, we're also teaching Frogger to speak like a human as well. And that gave us a whole bunch of data, 2,000 paired data sets that we could then train two systems, right? So first we had to train the agent to play Frogger. We actually made two versions, one that's called the focused view. This has basically a 7x7 window around it. Turns out this is actually all you need to build a reinforcement learner that can play a really good game of Frogger. But we also made a version of Frogger that could see the entire game board. You'll kind of see why we did this in a few minutes. And then we also trained the neural translation system, which is a sequence-to-sequence model, to basically take the observations and the text that were paired together and then try to learn how to translate observations to text. Okay, and to kind of give you an example of the sorts of explanations that we were able to generate after we went through this whole process, you can kind of see a few shots of some of the explanations that our Frogger would be able to come up with, both in the focus view and the complete view. And what you see is the complete view, the explanations tend to be a little bit longer and kind of refer to more objects on the screen. It reads pretty well. I think these are pretty fluent sorts of things. All right, but that all set us up with another problem. And I think this is kind of where things really got interesting for us, which was, how do we evaluate this? All right, there's no other systems that really kind of work like this. There's nothing really to compare against. But we realized that it wasn't actually what we didn't really actually want to beat some sort of benchmark. What we really wanted to know is understand what sort of effect do these explanations have on real people. So we went and we got real people. We did a human participant study. And again, our first thought was like trust, right? So do rationales help people trust their agent? Does it help them want to use agents more? But actually, we couldn't just ask about trust. Trust is a very complicated phenomenon. So instead we broke it down. We said, all right, there's a bunch of things that I think our explanations are doing that are related to trust. There are things like the confidence that the person has in the explanation. There's human likeness. People might perceive whether or decide whether the explanation is adequately justified, right? That it is a good justification, right? And is understandable. So like the grammar and the spelling and all that sort of things, all right? So these are the sorts of things that we then asked about. We said, all right, we're going to give you Frogger. You're going to watch Frogger. We'll give you 3 different rationales at any given time. One will be from our Frogger agent, either complete view or focus view. One will be an actual human explanation, because we remember we had got all that data, and one will be a completely random. Okay, and you will have to then pick which one you think is the best explanation in any one of these settings. Okay, so now the takeaways are, the explanations are pretty good, right? That's not the point, right? Random is a horrible baseline. The human explanations that we're up against are an upper baseline. So what we really wanted to know is, could we get the red bar as close to the green bar as possible? How close to the upper bound could we actually get? And we looked at the focus view and complete view. The takeaway here is you can kind of see from the complete view that we're getting closer to the upper baseline. So people were rating explanations from the complete Frogger a little bit closer to what humans were able to produce as well. So that's kind of nice, right? It kind of tells us we're in the ballpark, we're making good explanations, but this actually isn't really the point, right? We kind of knew this was going to happen. What we really came out of this with, which was, I think, what the really kind of the exciting results, not the algorithm itself, but what we're able to do with the data we collected from these human participant studies, we're able to take all the 4 things that we asked about, the 4 dimensions we asked about, and we also asked participants to tell us in every single case what things that they were thinking about when they made an evaluation, right? When they decided they had confidence, when they decided how human-like it was, when they decided how justified it was, and so on and so forth. And we did a qualitative analysis which came up with a number of additional dimensions that were human factors, right? Contextual accuracy was whether the agent was making use of the context around it, right? Awareness was whether it was making reference to things on the screen that were actually there. It's kind of like these two things are like faithfulness. Whether it was strategic detail, whether it was referencing its actions related to the things that were going on the screen, whether it was intelligible, readable, and whether it was relatable, right? And these are the terms that tend to come up over and over again when we ask humans what they cared about. And not only that, but we could actually kind of correlate these things to our trust dimensions, right? So confidence was a factor of contextual accuracy, awareness, strategic detail, and intelligibility. These are the things that made humans more confident about the explanations. Human likeness was a function of strategic detail, but also intelligibility and relatability. Okay, that sort of makes sense. That makes people think these systems are more human-like. Justification was a feature function of accuracy and awareness, right? Justification means these are the faithfulness terms. So we're getting good faithfulness because the agent was explaining these features. And understandability was about relatability, interestingly enough, and contextual accuracy. So now we have a much better idea for what humans find useful when it comes to explanations and how it relates to things that we might care about. Again, not trust, but the features that play into trust itself. But that kickstarted a process, because then we realized that there were all these human factors that we didn't know about going into our algorithm design. And the more we looked, the more we realized that we didn't really know a whole heck of a lot about what happens when humans read explanations. And so we started brainstorming some of the other things that we thought we might want to study. And one of the big ones that came up in almost every discussion was human differences, right? The fact that different people are going to have different opinions or perceptions of explanations dependent on their epistemic background, i.e., do they have technical backgrounds? Do they have computer science degrees? Have they even studied artificial intelligence versus people who've never studied computer science or gone to college or have kind of lower kind of educations, right? Educational levels, right? So specifically, we ran another study. We said, well, let's actually look at the same issue with Frogger and these rationales, but then now let's look at different types of users. Let's look at those with no formal computer science training versus those who are receiving a computer science training and have even kind of taken AI classes, right? And what do we then know about? Okay, so a few problems that came up. One is no one cares about Frogger in the real world. So we came up with a little bit of an artificial version of Frogger. We said, let's imagine that you're on Mars and you need a supply run and a robot is out to get the supply run and it has to return with valuable resources or everyone's gonna die. But in fact, our agent is just playing Frogger, right? Instead of cars, there's boulders, and instead of water, there's lava. Okay, so it's Frogger, right? This is basically just a way to kind of get people thinking about consequences, right? And this time we did 3 different agents. So first of all, I'll note it's the same reinforcement learning agent every single time. They just give a different explanation. So we had a rationale agent. So the blue one, you can kind of see the sorts of explanations. We've seen those before. We had an agent that simply declared the action it was doing, like I will stand still, I will go west, I will go up, I will jump, things like that. And then we gave it a numerical agent, which didn't do any sort of explanation except for dumped a bunch of numbers to the screen. And those of you in this workshop will probably guess that those are Q values. Those are in fact Q values. Okay, so now we wanted to basically say, well, does the form of the explanation affect different sorts of people with different technical backgrounds? And we did a whole bunch of analysis. This is actually, again, the least important thing. Basically, what this is going to show us is that when we ask about things like confidence, friendliness, intelligence, second chance, that is, will you choose to work with this agent again, and understandability, everyone liked the rationale agent best. That's the blue one. All right, that's not particularly surprising. We expected that, and that's what we got. But when we looked at the second choices, we saw huge differences between our two groups, our people with technical backgrounds and people without technical backgrounds. And without going through all the details of how we did this, we did a lot of semi-structured interviews with people. We came away with a few observations about how different sorts of explanations affect different sorts of people. Okay, and the first was something revolving around an unwarranted faith in numbers. So we saw this issue with numbers come up all the time. Remember, one of our agents is dumping numbers to the screen, right? So the people who didn't have AI backgrounds, who didn't have computational backgrounds, they, when it comes to their second favorite agent, they were pretty impressed often with the agent that gave numbers. They had no idea what these numbers meant. But it turns out they associated numbers with the presence of higher, more intelligent expression. Basically, if it sees a bunch of numbers, the agent must be really, really smart and it must know what it's doing. And I'm going to trust it more, which was quite surprising. Okay, so now we're all kind of have computational backgrounds and we're going to laugh at the non-AI people. But when we talk to the AI people, we also found issues with numbers. People with AI backgrounds associated the presence of numbers also with logic and intelligence, and more importantly, believed that these numbers were potentially actionable. That is, that they could somehow glean extra information if they just studied the numbers long enough. And these are Q numbers, so they tell you something about what the agent is doing, but Q values don't tell you a lot, right? You can't really kind of figure out a lot of the why questions. You can figure out a lot of the what questions, but not a lot of why. So people with a little bit of computer science background were kind of putting a lot of significance on numbers, way more than was justified by the numbers themselves. Okay, so that's another way of saying that different types of people have different biases when it comes to numbers and get tripped up in kind of different ways about the presence of numbers. We also saw different users come away with unanticipated explanatory value, right? So some of the people in the non-AI group really liked the action declaration agent because they saw it as evidence of what they called stable system performance. The text matches the action. Oh yeah, this agent must be operating correctly because when it says it went up, it actually went up. Now we know that it was programmed to say I went up when it goes up, right? And these are not two systems kind of checking each other, verifying each other. But people in the non-AI group didn't know, and so they trusted sometimes the system more because they saw this text as verification that there was some sort of intelligent process going on. The AI group, as we mentioned before, ascribed diagnostic values to numbers, right? If they could only figure out what these Q values are, they would somehow be able to fix the agent if it ever made a mistake, even when they couldn't actually do that. And then there were some observations about language and human likeness. Both groups basically found the rationale agent better, more relatable, socially relevant, and exhibit personality. Some people thought it was too talkative. Both groups rejected the idea of collaborating further with the numerical agent. Basically, everyone hated that agent, even though some of them thought it was the smartest sometimes. The non-AI group sometimes often kind of perceive the rationale agent and the action declaring agent as equally adequate. So really, when it came to the intelligence of the agent, which one's the smartest one, which one do you want to work with? They're like, I could take the rationale agent or I could take the action declaring agent, which was very, very surprising to us. And the AI group, was a little bit different here. They required more complex language. They knew better than to take the action declaring agent. They knew that more complex language is actually hard to produce. The non-AI group were like, language is easy. AI group was like, language is hard. So this told us a lot of things go through the heads of people when they read our explanations, and they're not always the things that we expect to have happen. Okay, so we spent a lot of time with this data, and we started also thinking about all the things that can go wrong, because there were some very surprising results here. Now, a lot of people have been talking about dark patterns. Dark patterns are intentional designs of systems that have negative effects. Some people have even gone so far as to say explainable systems can have dark patterns. We can get people to do things that they shouldn't do by using explainable AI systems if we design nefariously our explanation systems. But what we were seeing went a little bit different than that. What we saw was something that we call explanation pitfalls, which is that if we don't really understand how users are going to see the explanations as actionable, and how it's going to affect cognitive biases, then we might produce explanations that unintentionally have undesired effects, right? In the case where we did not expect some people to think that the agent was smarter, for example, because I had numbers on here, and yet we were causing people to feel like agents were smarter. Could that have caused them to put too much trust in a system that was failed, right? These are the sorts of things that could have happened because we were still in the process of understanding humans, not the algorithms, but humans. Okay, so we came across for some more conclusions, which is that it's going to be really, really important for consumer-facing applications. If we ever want to have explanations, we really need to study the effects of the explanations on our users to make sure they're doing the right things. And we should probably start doing something that's called seamful design. Now, seamful design isn't our idea. It's been around for a while. It's the idea that as designers, we should look for the disconnect between the system and the user's mental model of the system. This is also a concept that's come up different times throughout the day in terms of model reconciliation, for example, right? Figure out where those disconnects are and then design to those disconnects. Okay, and if we could do those sorts of things, we do seamful design, right? We might be able to make systems that have more effective, higher quality explanations that will not backfire on us or our company, right? So if nothing else, we might want to do this to protect our own interests when we deploy systems. Okay, so that was largely the kind of journey that, as you can kind of see from the dates of the papers, is we spent something like 5 years studying humans. We set out to study algorithms. We ended up figuring out that there was lots of questions that we had to answer just studying humans to begin with, in the presence of AI systems and explainable AI systems. And so the first part of my talk was really to kind of show you how we came to study these things and some of the important things we learned. It's not exhaustive set of things we learned and some of the conclusions that we came up with, because those conclusions themselves have helped us as we have looked at building algorithms. So we've studied humans. Now, what have we learned through this process and how has that helped us build better explainability algorithms? Okay, so this is for the people in the audience who, really want to see technical detail. All right, we're going to have technical detail. All right, and the first thing we're going to look at is seamful designs. Right, this has been a very important topic to us and has really kind of shaped the way we thought about what explainable systems are for and how we create explanations. And the one that I think is really kind of fruitful, well, I'm going to turn a little bit to natural language processing. And I know this is not an area that most of us are kind of comfortable with at this workshop, but seamful design is all about finding these points of disconnect between the user's mental model and the AI system on how it operates, and then trying to design a way to kind of fill that seam, to kind of bring out information that will be useful to the user. Okay, in terms of actionability, right? And so we spent a little bit of time recently looking at question answering systems with large neural networks. So these are the sorts of questions that are systems that'll answer questions like the one you see on the right. So what year did the band without Hussein with or without you form, right? And these large language model neural systems, they can often answer these questions, but they don't always answer the questions, right? And in this case, we're looking at multi-hop trivia questions. So these are really hard questions to answer. Most people don't know the answers to them. They have multiple parts, and so you can't just kind of Google this, right? But one of the things that we realized with these natural language processing systems is that a lot of people wanted to look at these systems from a system level sense of trust, which is, should I trust this AI? But with natural language processing systems, it's not always whether you can trust the system, but whether you trust the answer. So sometimes these systems are really good in some topics, and sometimes they're horribly bad. And sometimes they answer your questions right. And then sometimes they're talking about things that they have no idea and they're getting things wrong. And the same system can be right in some cases and terribly wrong in other cases. So we started thinking that maybe system level trust is not really the way we should be thinking about trust in our AI systems, but instead instance level trust, which is not, should I trust this AI, but should I trust this particular answer to this particular question? And how do we get the agent to do it? So first of all, I should note that We're going to ask people to guess whether the AI system is right or wrong. And then we'll make the AI system right half the time and wrong half the time, just for experimental purposes, right? So basically, humans were able to guess whether the AI system was going to answer the question right about 58% of the time. That's not a whole lot better than chance. I think they sometimes knew the trivia questions, but most of the time, really, our users were basically just guessing. All right, so where are the seams? How do we deal with this seamfulness? Okay, so what we did is we said, all right, we want the users to build a better mental model to guess whether the system knows the answer to something or not without being able to look inside. So we're going to train a second neural network to decompose the question into sub-questions. So we're doing something called probing, which is basically I'm going to make a whole bunch of other related questions, and I'm going to throw them at the agent. And I'm going to show people both the sub-questions and the sub-answers. And the idea is that we would hope to expose the internal competencies of the agent. So if it's starting to get a lot of these sub-questions wrong, then we might question whether the agent knows what it's talking about. So these sub-questions are hopefully verifiable by the participants. But even if they're not, they're at least something that are easier to verify, right? These sub-questions can be Googled, for example. So we can test the agent and then we can verify it, because even if we can, and that'll help us understand whether we should trust the agent on the original question or not. And I'm not going to spend a lot of time talking about the models or the data sets or anything like that, but just to kind of give you an idea of how we went about building a seamful system, right? We were able to increase participants' ability to guess whether the agent was wrong or right up to 63%, which is somewhat modest, but it is statistically significant for our number of users. Okay, so this kind of tells us that exposing more about the system's competencies does help in some ways. Humans do a better job of deciding whether to, trust is a strong word, but decide whether they want to accept the answer that an AI system was given. Okay. So we did that in natural language processing, but we also wanted to do this in reinforcement learning as well. So this is a planning workshop. I should probably talk about planning or reinforcement learning, right? So for all of you who are holding out, hoping to hear more about reinforcement learning, here's the technical part. How do we do explainable reinforcement learning, right? So one of the questions that I think, again, people ask questions when they have a misunderstanding of what the agent is doing, right? And it's going to be a question along the lines of why did an agent do X or why didn't an agent do Y, right? But let's look at why did an agent do X. There's lots of different reasons we might be able to get, lots of different ways we might explain this. It could be because after 1,000 interactions with the environment, it was determined that the action has the highest future expected reward. That is an explanation. It's not particularly actionable. I don't know what to do with that. It could be because the features are present in my observations that correlate with predictions of high utility. That's a little bit more useful, right? It can tell you what the agent is paying attention to and how it's making decisions on what it's seeing, right? So that's a little bit better. But what I really wanted to do was kind of get back to this idea of stories, right? And goals. So an explanation might be because I need to do X so I can do Y later. Remember, reinforcement learners are about the future, right? It's doing something, and it's often not that it's doing something because there's some sort of local condition on the ground. Sometimes that's the case, but oftentimes it's making a decision now because it sets up some sort of future consequence that's actually even more important, right? So what is it that it's trying to set up in the future? And does understanding that about these goals that the agent might have or sub goals, is that helpful from an actionability standpoint for people who are actually going to interact with, again, consumer style reinforcement agents? Okay. So not going to do Frogger this time. We're going to do something called text adventure games. This is a game called Zork. And text adventure games are basically played by reading text and writing text. And just to kind of give you an example, this is the game Zork, and I'll kind of tell you what's going on the screen here. At any given time, you're in a particular state. It's partially observable, tells you what you can see at any particular moment. So for example, you're on a forest path. There's a path winding through the dimly lit forest. So it's describing some things about the path and what you can see. Can't see the whole world. You can just see a little bit of information about where you are now. The user or the agent is able to type in commands to do things like climb tree, go north, go west, pick up objects, take objects, so on and so forth. And when you do that, your state changes. You get a new description of your new state, and then you can do additional actions from that point going forth. So this is a Markov decision process, partially observable Markov decision process, and it is a particularly challenging problem for both humans and for AI systems to work in. So how do we build a reinforcement learning system? Before we get to explanations, we have to figure out how do we build reinforcement learning systems that can play text adventure games to begin with. Well, you can kind of see you have game descriptions on one side. Based on those game descriptions, you have to perform some sort of action in natural language, pseudo-natural language, I should say. So the way you kind of decompose this problem is you say you're going to start with a game description. You're going to construct some sort of model. You're going to manipulate the model and then choose the action, right? Should be too terribly surprising. This is what humans do. So when humans play these games, we get out a piece of paper and a pencil and we start charting what we know about things and how things are related and where inventory items and so on and so forth. So we're going to take that as an inspiration. We're going to basically say, as we play the game, we're going to build up something called a knowledge graph, which kind of has all the information about all the items and objects and entities we've seen and their relations to each other. So behind the house, locations, objects, so on and so forth. And then we're going to throw this representation into some sort of neural network architecture that's going to tell us both the action and the utility value. And I'll talk about what this neural network does in just a second. The agent that we're experimenting with is one that's called Qbert. So 10 extra points for everyone who figures out why it's called Qbert. It works like this. You start with some sort of description about where you are. That's your observation. You feed this into a system called Albert QA. It's basically a version of BERT. It's a natural language processing system, and it can answer questions. Questions like, where am I located? What is here? What do I have? So on and so forth. From that, we can induce it to give us basically the entities and the relationships between those entities. So the window, the house, the path, the egg, so on and so forth. We update our mental model, the knowledge graph. We feed this into a convolutional attention network. We also encode the text through a recurrent text encoder. We throw all this into a two-headed neural network called an actor critic, which is going to basically predict the action and the value. Okay, so this is not particularly easy to explain. We all know that neural networks are hard to explain. So we augmented the Qbert agent to something called HEX-RL, hierarchical explainable reinforcement learning. We've made the following changes. We threw away a lot of the knowledge graph stuff, and instead we have a decomposed knowledge graph. Basically, we have a knowledge graph for all the locations, objects, players, and attributes that we observe. We basically keep all this information separate. We encode each of those separately through graph attention. We add all that graph attention, and then we slam it through the actor and the critic. So interestingly enough, so we're doing this for two reasons. One is so that we can look at explanations involving locations and objects and attributes kind of separately. But second of all, this actually caused HEX-RL to do better on Zork than Qbert. So this is one of these really exciting cases where trying to get a system to be more explainable, we actually made it better at doing the tasks to begin with. And that's always a win-win when your explainable systems are actually better at their jobs than non-explainable systems. But what can we do with these decompositions? Well, we're going to do two types of explanations. We're going to do local explanations. What we call local explanations. And local explanations are basically going to use the graph attention and say, which of the concepts in the graph are the most important for the action that's being performed, right? Think about this as heat mapping over a graph. Okay, so standard attention mechanisms. And that can tell you things like, I open the window because it has the property being openable, for example, right? That's useful information. But maybe not exactly what we wanted to do. And so we also look at things beyond the neural network. We also looked at something called temporally extended explanations, which attempt to answer what I think of as more of the why questions. Like I want to ultimately answer a question like, I open the window so I can lift the rug in the living room. Okay, so that's something about doing this so I can do something else later. And I'm not going to go through all the details because we don't have a whole lot of time, but basically we're going to, as we train the agent, we're going to keep track of all the states and trajectories of states, these traces of states over time. And we're going to use a combination of a Bayesian analysis and some other things to basically figure out which states correspond to future states that are semantically related to each other. Basically, what I'm doing is I'm looking at all my future states and saying, which is the most likely goal that I'm trying to achieve for any particular action that I do. Okay. And to kind of jump to the chase again, to get to the results, you can kind of see on one side the sorts of explanations that we can kind of generate. And on the other side, we asked people to rank different explanations from looking at both the immediate explanations and the temporal explanations, looking at whether they find their confidence, human likeness, understandability, readability. These are all some of the similar questions we've seen before, but we added an extra on, which is, does it help us understand the goal of the agent? And all the numbers are somewhat equivalent. Green is higher, which means our temporal explanations are always preferred slightly more than immediate explanations, except of course in the case of goals, which we can basically say that goals are important and we are able to achieve higher preferences for understanding goals, obviously when we do temporal explanations. So that's perhaps kind of somewhat expected because we asked the question to get the answer. We kind of, well, not that we did that, but we wanted to know whether people do perceive differences in terms of goals. So that means they do, that's important to the users. All right, and that's just the same thing highlighted. All right, last bit before I nod off here. Remember I started with stories, right? I think explanations should be stories. Now I want to return to, but we never quite did that with Frogger, right? We never got to, we got to instance level sorts of things, but we really never got to stories, explanations and stories. So we are finally at the stage where I think we're able to do this. I'm going to talk a little bit about ongoing work that I think is really exciting and something that we're calling experiential explanations. And these are explanations that are designed to answer counterfactuals. So in other words, why didn't you do X? So again, the same grid world we saw before, why didn't you go down? Why did you go up, right? Is another way of saying, why didn't you go down? I think I have a mental model that said you should have gone straight to the goal. Why didn't you go straight to the goal? Well, it's probably that the human doesn't understand the significance of particular parts of the state. Now, of course, the agent has also forgotten the consequence of the state, right? So the policy network doesn't know why the Q values are the way they are once it is done learning. So what we need to do is we need to help the agent recover its understanding of why Q values are higher in some cases and Q values are lower in the other cases, and to be able to convey that to users. All right, so to do that, we're not just going to learn a policy, but we're also going to learn to predict the influences of certain states, reward states, on the utilities of other states, right? So we can look at the goal and we can kind of see, the goal has influences in terms of utility. It's better to be closer to the goal than further away from the goal. But of course, it's also better to be further away from the stairs than closer to the stairs, and further away from the rough floor than closer to it, right? So given a counterfactual trajectory, like why didn't you go across the bottom of the screen, can we identify the states that cause decreases in expected reward, right? So you can get to the goal, but a lot of those states are being influenced by the stairs. There's some probability, in other words, that stairs are going to cause a problem. And furthermore, we're going to ascribe language to these states. We're going to say that the stairs don't even not only give you a penalty, but also give you a piece of language, like I fell down the stairs, or I might fall down the stairs. And that by kind of looking at different trajectories, counterfactual trajectories, we might be able to analyze this and say, all right, well, based on the way that you thought the agent should have gone, I can tell you that there's an issue with falling down the stairs because some of the states are being strongly negatively affected by a particular state that gives us a particular piece of information, right? We stitch all that information together and hopefully we're going to get explanations like I didn't go down because I might fall down the stairs. So this is work that's undergoing. I hope to be able to share some of this a little bit later in the future. And again, actionability is something that comes up. Why do we want to do experiential explanations? Well, because I think it can answer two things for participants. One is that the participants will hopefully be able to identify interventions that would cause the agent to do things. Like if you really wanted the agent to go up, how can you change the environment so that the stairs are less of an influence, right? Put up a gate, close a door, something like that. And also, I think ultimately we'd hopefully be able to show that these sorts of explanations, these experiential explanations that explain what the agent is going to experience if it does certain things, will ultimately help the users adjust their mental models so that in the future, they're more able to predict what the agent is actually going to do. So ultimately, I think the best answer here is when you don't have counterfactual questions, it means that you have a human that is well aligned with the agent and what it's capable of doing. Okay, that was a lot. I want to leave you with just a few additional thoughts. And one of these is about our community. So there's a lot of people now talking about, and there's this narrative developing that explanations are not useful, that explanations are a waste of time and effort because they're not helping and they're not working. So just an example, this is something that was published not too long ago, looking at healthcare explanations and how healthcare explanations are not improving patient outcomes. Well, at the surface, that sounds kind of bad, but there's actually kind of something going on here, right? So these AI systems are often being developed that aren't really meeting the needs of doctors or patients or anyone else. And the explanation systems that are being added onto these systems in the hopes of improving the situation aren't giving users what they need. They're not giving them actionable pieces of information. And so I think a lot of these systems are failing because we're not understanding who the user is and what they need and what is actionable and what we need to give them to be able to make better choices about AI systems. I think this is a failure of human-computer interaction. And I don't want to throw out the baby with the bathwater and say explanations are not working anymore, but I think we need to rethink the fact that maybe we're not asking the right questions and that looking more towards our users are going to help us design systems better. And the way we might do this, there's lots of ways we might do this. One is called critical technical practice, which basically asks us what assumptions are we making when we work on computer systems, when we work on algorithms? Are we making assumptions? And do those assumptions kind of lead us away from the questions we should actually be asking? Okay. We also need to be asking whether explainability lies in the technology. All right, is explainability coming from the technology? Is explainability coming from humans? Or is it some sort of combination of the user and the AI system working together to co-create some sort of understanding? Okay, we need to think about these things as we build, again, consumer-facing technologies. Is trust the right goal of explainability? Should we seek trust, or is trust in some cases even harmful when we trust systems that aren't worthy of our trust? And do our explanations create trust when we shouldn't create trust? What sorts of actions do explanations afford or inhibit? And ultimately, I think we should be doing something called participatory design. We should actually be working with our stakeholders to design our explanation systems, to figure out what they need out of the explanation systems, and then we're actually giving them to them. So I'm working with radiation oncologists this fall, and I hope to be able to share some kind of design practices on how to work with our end users to build explainable AI systems. And so just to kind of wrap up here, explainable AI is really exciting, but it's also a young and it's a rapidly maturing field. We don't have all the answers, right? And as we rush to build AI systems and explainable systems, we're going to make mistakes. That doesn't mean explainability doesn't work, but it means we do need to revisit the assumptions that we bring with us when we build explainable systems. Not all explainability has to be human-centered, but when it is equal parts AI and HCI, so it's implicitly multidisciplinary. We need to be asking questions: what are explanations for? How do people want the explanations? What sorts of people need different sorts of explanations? And is it helping them do things that they weren't able to do otherwise? Are there generalized properties of explanations? And how do we even know when an explanation system succeeds? And ultimately, I think that as more AI leaves the lab and goes out into the real world through applications and services, explanations are going to be increasingly growing an important part of what we do as AI researchers, especially if we want to have customer-facing impacts out on the real world. And I think that people are not going to adopt systems the way we want unless they're explainable and unless we give them the explanations that they ultimately find satisfying and actionable. And so with that, There's a whole bunch of people that have gone into this thinking. I'm not the thinker here. I'm just the person who gets to talk about other people's exciting work. I want to highlight the first 3 people on here: Upal Ehsan, who has been especially important in all this work, Sarah Wagrefe, and Raj Amarabolu, who will be on the faculty market soon. So keep an eye out for them, and all the rest of my great team. And with that, I hope I haven't gotten too long. I got very excited about this, and I'm super excited to answer any questions that you all might have. Thank you very much.
Thank you so much. So I think we're ready to take questions. So I have quite a few, but maybe I'll see.
I love answering questions. Go for it. I'll let you moderate.
Yeah, maybe I'll just start. But if anybody else wants to ask, please raise their hands. Oh, there is. Maybe I'll let Eric start. Okay.
Hi. Thanks. This was really interesting. And so you kind of mentioned this, right? But when you talk about actionability, right? Mm-hmm. So the notion of actionability means I can give any explanation I want, as long as it makes the user adopt the system, right? And obviously we want to constrain that to correct or truthful explanations, right? But my question is there some notion of a correct or truthful explanation or something like that?
Yeah, no, this is one of the things that makes things very challenging, right? So is there correct or truthful explanations? I think there's multiple things we need to look at. I think faithfulness is the term that the natural language people are starting to use. I like that term a lot, so I've started using it myself. So are they faithful to what the agent is doing? We can't have explanations that lie, right? That say something that's happening and that's not actually happening. That's particularly problematic. That's one of the weaknesses of the rationale generation, and why they explain the stuff towards the end to try to actually kind of get into the algorithm itself, open up that black box to ensure the faithfulness that we're actually using the numbers being generated by the system, for example. So I think we do want faithfulness, right? We don't want lies. But I think that's also tied to, actionability. So actionability is, does it help users make choices about what they get, right? And sometimes the choice is, I don't want to use this system anymore. Sometimes it's, I'm going to use this answer. Sometimes it's, I'm going to, I'm going to call the developer, or I'm going to, do some sorts of things. And it's not entirely clear. I don't think we have a good idea of what actions are, what actions they want. So, but I think if the explanations are opening up the action space for our users, then that is also beneficial. I think the more actions our users have, the more actionability that is afforded by an explanation that wasn't there previously, means we're doing something right. Now, throw in dark patterns and pitfalls and all those sorts of things. We don't want those actions to be against their own intentions, right? So it's multidimensional. I think you're hitting the nail on the head with what all the research challenges are, and the complexities of these.
Thank you.
Yep, absolutely.
I think the raises hand next.
We have the floodgates have opened.
Yeah.
That's great. I want to answer questions, please.
I had a really interesting talk. I had a lot of fun listening to this. I had a quick question on the Frogger experiment. So in the evaluation of the 3 kinds of experiments, was there a prompt for an explanation from the user, or the explanations were always provided? Because I imagine from the seamless design perspective, the requirement from an explanation will only arrive if the user thought there was something wrong. If everything is right, then I guess the Q values would appear more reasonable if things are going all right.
Yeah, so it's a good question, clarification question. So in that case, we always gave the explanation. So in some sense, our Frogger was just talking out loud all the time, whether people wanted the explanations or not. And that that was partially an artifact of the experimental design. We wanted people to basically have a lot of options to both kind of rate the explanations, but also every time we gave an explanation, people were able to type in, basically why they thought one was better than the other. which was what gave us all the qualitative analysis, which ultimately was the information that we really wanted. So I wasn't particularly interested in whether we built the Frogger system right or wrong. I wanted to know what it made people think about when they saw different information presented in different ways.
Right. But do you believe that if, well, let's imagine it's not a Frogger system and it's something that's
an
actual role. Would it make a difference? Do you expect there to be a difference?
I don't know. I think there would. I don't know if there would be a difference in what people prefer or what people thought was important about the explanations. But the fact that people ask for an explanation is actually signal itself, right? Because people don't ask for explanations unless there's some sort of disconnect in their mental model about what the agent is doing, right? So I guess that's a great research question that we'll have to look into.
Yeah, thank you.
Thanks.
I think the next one was Ben.
Thanks, Mark, for the talk. I thoroughly enjoyed that. My question is actually to Tatagatas, but maybe a little different. So with the Frogger experiment, I mean, I agree that I think that we need to look at explanations from a user-centric point of view and see what they want to be explained before we go about trying to find explanations for certain things. Now, when it comes to quantitative user studies, you see a lot of different literature that says, you get data saturation at very low sample numbers. Now, when it comes to kind of more complex domains, so for example, on the Frogger domain, you had 60 participants, and I'm sure you probably reached some sort of saturation in the types of explanations that the users gave when they were playing the game. Now, do you think that saturation will, you won't necessarily get saturation with those low numbers on much more complex domains? Do you think that the types of questions that users ask about any sort of domain might transfer over between, for example, the Frogger to a complex robotics domain or anything else as well? I wonder if you could talk about that.
No, great question. I mean, obviously, it was a simple domain, so we didn't need a lot to get that. And yes, right. So it's saturated. We can tell you that because we did the qualitative design. We iterated until we got saturation, right? For more complicated domains, I think that at the high level, there's probably a fixed ontology of the sorts of questions people want to ask, but the details can be very different. If there's any, and would that saturate? I don't know. I think it, like once the detail, let's take the question answering systems, right? If you can ask any sort of question to an AI system, then, you're going to get a lot of varying things, and those things are maybe not going to overlap particularly a lot. So maybe you don't get that in those sorts of situations. With robotics, maybe yes, because, why did you break? Why didn't you do the thing I was expecting you to do? At the high level might, kind of, there might be only a smaller set of things that people really actually care about. But I do think the broader issue here that we thought a little bit about and we don't have a good answer for is we really can't predict what people use AI or robots for in the future, right? I don't think anyone really expected people would put cats on Roombas, right? And so different uses are going to convey different sorts of questions and different frustrations, because now you're using the system for a way that the developers didn't even anticipate for, and therefore the explanations are not going to anticipate as well. So that is a technical challenge, right? So, which is now call it like open-ended explanations or something like that, right? Yeah, so I don't have, I can't go deeper into that, but I think there is an outstanding issue about use and misuse and unexpected uses of AI systems. So why is the person trying to use the AI system to begin with, right? I mean, who knows, right? Whether they trust the answer is going to be hugely different whether they're playing trivia night at the bar or whether they're trying to, decide what stocks to buy, right? And what is actionable is going to be very different. And therefore what they want to know to encourage actionability is going to be super different. So I guess I'm asking questions back to you and to the entire community.
Yeah. I mean,
but it's a really great thought.
Yeah, I mean, I was just wondering if you have any kind of recommendations going forwards, like how people should approach dealing with that. I mean, obviously, you wouldn't want to have to run a study of that sort every time that you're going about trying to create some explanation interface for an AI system. However, you probably still need to take that into account because, as you said, you want to go from the human to the algorithm and again back.
Yeah. No, I mean, what I would hope is that there are principles of human factors in the presence of explanations that are universal, and that they're not too high level to not be useful, right? And those will guide us in terms of what we then need to dig into. But it might be the case that every system that we build, there's certain principles we can rely on, but there's certain things that are going to be super specific to our application that we're not. And this is something that comes up in human computer interaction all the time, right? We look at this system, we can't guarantee anything we've learned from the system will work on the next system. And I would say if there's developers, people who actually develop these systems in companies, right? I think they're the ones who need to kind of, check to make sure that they're not relying on things that are not generalizable. So they might actually need to do those studies.
Yeah. Okay, great. Thank you, Mark.
Great discussion. Thanks.
I think Marcel had his hand next.
Yeah, hello. Thank you. Yeah, I was wondering if you could expand on, at the very end, you teased some work, where you're doing this counterfactual explanation generation I was wondering if you could expand on how that's done. I guess for context, I've worked on doing things for learning from demonstrations, like learning programs from demonstrations that uses at least superficially similar set of ideas. So I'm curious how that's.
Oh yeah, what do I want to say about a paper that hasn't come out yet? We're not using demonstrations. We're developing techniques to basically play with the internals of our reinforcement learning system to basically, all right, neural systems do prediction, right? So it's trying to predict the influences. So not only how does the Bellman update your values, but what are the things in your environment that are probably causing your Bellman values to change more or less down there. So we're basically layering a bunch of influence predictors in addition to your standard Q learner. It's actually not Q learners, PPO, but that's probably at a high level what we're trying to do. In other words, the agent is learning to do its own analysis of its environment and what causes its policy to change.
Great, thank you. Yeah, that's helpful.
Amal's here and she didn't know I was going to talk about her system, so I hope she's not horrified at me.
So I find the issue of truthfulness in explanation to be very interesting, because in a lot of cases with more complex questions, you end up resorting to an abstraction, right, to actually answer the question, an abstraction of the problem, and by their very nature, abstractions are convenient lies. And so I'm wondering if you have any thoughts about how you assess the veracity of an abstraction.
Yeah, no, great question. So there is a body of work on testing faithfulness. As you can see, I often kind of stop a little bit short of this. I basically say there's strong correlations between what's going on in the algorithm and what's going on in the abstraction in the language, right? But that doesn't, again, guarantee. There are people, and I'm going to draw on some of the work in natural language processing, where they have looked specifically at trying to figure out how to concretely measure faithfulness. And one of the ways you can do it is you want to show that there is stability in your outputs when you adversarially attack the model. Okay, so does your explanation change when I screw with the weights of a neural network, or when I throw noise into a neural network, or things like that? And so what you're trying to do is you're trying to basically trick a system to giving you what you know is a wrong explanation for the right answer, or vice versa. And if it's really hard to do that, then your system, you can at least say it's that is using what's going on inside the data, inside the model, to produce that explanation. So that's kind of a potentially a hard to understand kind of answer, but kind of gives you a gist of how you might do it. In other words, can you prove that your explanation is coming really close to the source of the decision itself?
Now, I noticed that you also didn't make any attempt to try to model the users themselves, right? And so if you're giving an explanation to somebody who understands physics and somebody who doesn't, right, the abstraction that you use with respect to those two people may be very different.
Yep. Yeah, no, that's a good observation. My own personal explorations of these areas have not been mature enough to go so far, but I would say that would be a really kind of interesting and exciting thing to do. And then whether you can then build an explanation system that takes model parameters or in, right? One of the issues is data, right? To train a system to do explanations in the Frogger way of doing it, for example, I would need to basically have an extra dimension in my data for all the different kind of personal dimensions or values, variables inside that user model. And so learning those sorts of explanations would require a lot of data, would be very hard. Heuristically or some other way might be possible. But I would say that'd be a great thing to try. So I'm just kind of here to tell you all, there's lots of exciting research problems that you should try. And you should publish them, and then you should tell me about them.
Thank you so much. So I have like few more questions. My chance.
Happy.
So some of the questions, my questions already got asked. So one of the points I just wanted to revisit was this idea at the end. You had this idea, we were talking about how to help the user build the right mental models about the system, right? You talked about, in the counterfactual case, you kind of know what the user has the right mental model for this. Stop asking questions. And then earlier on, you had this Q&A system, which is, the way I understood it is, it's in some sense showing certain behaviors so the human can form the right kind of mental model. That's the right kind of product, more or less. So do you see this as being a preliminary stage where before the user starts using the system, is there going to be like a training process where the human can form this kind of, that how you envision these kind of like interaction going forward? Those are maybe kind of
Yeah, I was having a little bit of hard time hearing. So let me see if you're asking if, is it similar to David's question in that you kind of have to have an agent know a little bit about the user beforehand?
Yeah.
Or
so I was more asking about the question about like your work on the Q&A system, where the way I understood it is the system was in some sense breaking down some of the answers. Like there's, like, I'm assuming it's based on some kind of curriculum that they select certain questions and show, okay, here are the answers, right? So in some sense, I'm thinking that in some sense, like a training phase for the user, so they get the right kind of mental model for the system. Is that the right way to characterize it? And do you see that kind of a training process as being needed for most like complex enough AI system where trust is going to be an issue, where the user has to spend some time building?
Well, I mean, that's an interesting observation, interesting question. I mean, there's always been a very strong relationship between explanation and education or training or teaching. And so, in some ways, all of this may be about or could be about, an AI literacy thing. Now, I don't think that you necessarily want to teach everyone, here's how a neural network works, and this is what it was trained on, and this is why you shouldn't trust it when it's asking questions about bands or something like that, right? But I do think the more you use a system, the better you come to understand its capabilities and what you can and cannot do with the system. And so the question is, do you do that up front, or does it just kind of come online in a fashion? And in that case, what the measurement is, how fast do you bootstrap people up, and should there be kind of additional things that agents should do versus just, hey, ask me questions. And these are really interesting kind of new perspectives on explainability as well.
Right. So I think part of my question was kind of trying to connect to things like the things that you were kind of pointing to, things like automation bias, right? People overtrust system, thinking system has capabilities it doesn't. Right? Yep. And explanation could, in some sense, feed into those kind of phenomena, right? It could give you certain explanation, and people over-generalize those explanations. So could those kind of issues be, in some sense, managed by this preliminary training phase? So it doesn't have to be for all kinds of systems, right? You don't really need this kind of a thing for like a Roomba, but maybe if you're like a mission critical system, you're using some kind of critical system.
Right. Okay. Yeah, I see what you're at. Yes. So I mean, trust calibration is kind of the thing that I was thinking about with the Q&A system, right? So we don't want people to overtrust, or we want people to trust appropriately, right? And the seamful design there, the probes were basically a way of kind of wedging into the system and pulling out things that the system doesn't naturally want to expose, right? It doesn't want to do more than answer a single question. So we make it ask 10 questions, right? In the hopes that, there's some sort of correlation between its ability to answer all these questions. So we're I call it probing because we're looking for flaws, right? And we're trying to expose these flaws, because if we do it right, then people will kind of say, all right, there's things that make me uneasy about what's going on in the system. And so maybe I need to be more reflective about what the system is telling me. Like, you got the answer right, but you got it right for the wrong reasons, or things like that are going to be important going down the road. And then teaching people, I think, that to look for these things and understand what they mean is also kind of part of it, to kind of tie the first part of the question back.
So the final question I had about the whole thing was because in the end you can't expect the system to show all behaviors because it's too complex for the way. So you need a intelligent way of doing these projects, right? You can't even expect the user to ask the probing question because they wouldn't know where to start. So have you thought about how do you design a curriculum for this kind of probing where the system can expose the right kind of behavior?
Yeah, this is why I talk a lot about design, right? That explanations aren't innate to the algorithms necessarily, but they're things that we design as layers on top of the system, or we add things to the system so that we can probe them in particular ways or poke at them, right? So there's still going to be an aspect of getting the balance right. I've seen papers that kind of show like too much information actually causes people to turn off and not look at the explanations at all, right? But not enough is also kind of bad. So, is this an application specific answer? Like, for these applications, you need to do this and that and not the other thing? Or are there some general kind of design patterns that will flow out of all this research that we can kind of use as starting points? I think these are things that we don't know. And I think, one of the important things, and the reason why I think HCI is very important here, is because human computer interaction people kind of really look at the design processes. They don't look at the algorithm or the final artifact, but they look at the process, who built the artifact, what went into it, how was it designed. These are all kind of studyable things and potentially tie really closely to the algorithm, right? So again, I talk about developers, right? But if you're in a company, right? You're going to be making decisions in the design process, the design stage of these algorithms. They're going to have profound downstream effects on your users.
Thank you. That's really helpful. I don't think we have other questions at this point, but thank you so much for coming to the workshop. And it was a really good. Thank you so much. So,
my absolute pleasure. Yep.
So it's always weird.
I know.
But yeah. So this brings us to an end for the first day of XAIP. So XAIP is like a 2-day event. So I think Professor Riedl is going to be back for the panel tomorrow. So I hope to see everyone there again. Thank you again.